Shall we start now? All right. Hello, everybody. This is YouTube from KAIST. Welcome to HotStorage 2021. I'm the co-chair of the HotStorage this year. Shall we start now?
Yes.
Okay. All right. All right. Hello, everybody. This is YouTube from KAIST. Welcome to HotStorage 2021. I'm the co-chair of the HotStorage this year. First of all, Phil and I, yes. Okay, all right. All right. Hello, everybody. This is YouTube from KAIST. Welcome to HotStorage 2021. I'm the co-chair of the HotStorage this year. Oh, okay, sorry. I have been running my speech through the YouTube as well as Zoom, so that was a delay. Sorry for the noise. Let me start from the beginning again, and sorry about that. Hello, everybody. This is YouTube from KAIST. Welcome to HotStorage 2021. I'm the co-chair of the HotStorage this year. First of all, Phil and I would like to thank each and every one in our storage systems community to make HotStorage 2021 to happen and to make it possible to continue its legacy. This year is a transition year for HotStorage in several ways. This is the first year HotStorage has been sponsored by the ACM CGOPS instead of Usenix. And we are grateful for their support and giving HotStorage a new home. Next, like many conferences, HotStorage was impacted by the COVID-19 pandemic. This caused us to hold HotStorage as a virtual conference, though there are hopes to meet in person again in the future years. HotStorage overcame many obstacles this year, and its continued success is a testament to the dedication of the steering committee as well as the numerous volunteers that made HotStorage possible. Most of the organizers were new to their roles, and everybody eagerly picked up the necessary tasks to make HotStorage happen. Phil and I would like to thank the researchers who submitted their early stage ideas to HotStorage. Without their research, HotStorage would not be a success. We want to thank our industry sponsors for their financial support. We earnestly hope all participants enjoy the venues for the next 2 days. Thank you very much.
All right, so again, welcome to HotStorage 2021. I'm Philip Shalane. I work at Dell Technologies. So we have over 250 registrants as of this morning from approximately 12 different countries. Some are joining us through the Zoom webinar and some are joining through YouTube today and tomorrow. Either one is fine. So it is a 2-day event. We will have 4 paper sessions, 1 keynote and 1 panel discussion. The keynote is immediately after this presentation. And so our 4 sessions include topics such as flash storage, distributed storage, new technologies, and characterization and verification.
We have distinguished keynote speaker, Dr. Sang-Yeon Cho from Samsung. He is Senior VP of the Samsung Memory Systems Division. He's currently working on enterprise solid-state drive development programs. He's going to talk about the works published at the prestigious venues as VLDB and ISCA, as well as the recent issues the storage industry is facing, such as QoS issues in multi-tenant settings, ZNS, host storage collaboration schemes. The keynote speech will start immediately after the welcome session.
So tomorrow, we are fortunate to have a very interesting panel session, From Ideas to Products, the Path of Successful Storage Startups. We've recruited 4 founders to join us, Hyunjin Park, Hugo Patterson, Niraj Tolia, and Hakeem Weatherspoon. Not only did they found their new storage companies and are growing them, they're in various stages of growth at this point, but they also all have research backgrounds. So I think it'll be a very interesting discussion about the growth of their startup companies, as well as the role that research and the research backgrounds played in helping them. And again, that is tomorrow.
This is facts about HotStorage 2021. This is first year transition from Usenix to ACM. We have 39 program committee members. 11 of them are female and 28 are male. We have 12 PC members from the industry and 27 from the universities. Each of the PC members has reviewed 5 papers, and we have a week of online discussion. And then we have online PC meeting to discuss to select the papers.
So we had 40 submissions. They represented 22 from academic, 4 from industry, and 14 papers that were collaborations of academic and industry from 14 countries. In the end, after our lengthy review process, we accepted 15 strong papers. 8 were academic, 3 industry, and 4 were collaborations from 6 different countries. So we know that there is an issue right now getting access to the papers, and we've contacted the ACM about that, so they are aware and are working on the issue. So the plan is that the papers will be freely available through links from the HotStorage website for a month. So if you're interested in downloading the papers, please do so. After that, the papers will be permanently available in the ACM digital library.
Thanks to our industry sponsors, Intel and Samsung, we were able to prepare 2 awards for the accepted papers, the Best Paper Award and the Best Presentation Award. For the Best Paper Award, we have formed Best Paper Award Committee, and the Best Award Paper Committee have selected 3 excellent papers as candidates for the Best Paper Award. They are Senilog, anomaly detecting a parallel file system via log-based sentiment analysis. The second one is isolating namespace and performance in key value SSDs for multi-tenant environments. The third one is how the common retention acceleration method of 3D NAND flash memory goes wrong.
All right, so our committee met and reviewed these 3 papers and considered their strengths. And in the end, we selected how the common retention acceleration method of 3D NAND flash memory goes wrong. So this is our best paper for HotStorage 2021. Congratulations to the authors, Q Li, Minyi, Tewei Kuo, and Chun Jason Zhu. Again, this award is sponsored by our gold sponsors, Intel and Samsung. And so their talk is today in session 1, immediately after the keynote at 8:25 a.m. Pacific time. And we will contact the authors later about receiving their award. So again, congratulations to the authors. In the background, one of our organizers, Luna, has been contacting ACM about the publications, and she just alerted me that they should now be available. So thanks to Luna and all of our organizers for working on this very quickly. So the paper should be available now for download.
And for the Best Presentation Award, we have carefully reviewed the style of the presentation, succinctness, the quality of recording, and the presentation style. We have reviewed all 15 video recordings, and the winner of the Best Presentation Award is DNA Archival Storage, a bottom-up approach by Omar S. Salah, University of Cambridge, Amar Appelbaum, Thomas Hines, and Jasmine Quat from Imperial College London, Andrew W. Moore, University of Cambridge. And again, the award is sponsored by our gold sponsor, Intel and Samsung, and they talk as tomorrow at session 3 starting from 7 a.m. PDT. Congratulations, the authors.
So I want to thank our program committee. Again, we had 40 program committee members representing universities and industry around the world. And I want to thank them for volunteering and providing their time and their excellent reviews on the papers, as well as serving as shepherds for the accepted papers and serving as session chairs today and tomorrow and guiding the discussion on the papers. In particular, we want to recognize our distinguished program committee members. We want to recognize those who gave especially strong reviews and for volunteering in various ways. Ramnathan, Janki, Shomali, Youngri, Yu Jung, Ju Young, Myung Soo, Stephen, Keith, and Gala. Thank you again.
And we'd like to thank the organizers. Without them, the HotStorage 2021 has not been possible, and including General Chair Vasily Asarov, Publication Chair Luna Zhu, and Publicity Chair Ali Anwar, and Registration Chair Travis Jensen, Sponsorship Chair Umesh, Virtual Workshop Chair Dimitris, and Web Chair Lucas. And also would like to thank all the steering committee members to make this to happen.
Again, we'd like to thank all of our sponsors. We are sponsored by ACM SIGOPS, and again, the papers will be available in the ACM Digital Library. We are in cooperation with Usenix. They gave us some support this year. Our gold sponsors financially were Intel and Samsung, and they both have channels within Slack, and so you could communicate with them directly. And we also want to thank our silver sponsors, Dell Technologies and IBM. And then finally, we'd like to acknowledge our support from the SysStore community, in particular their organizers this year. They gave us a lot of guidance and examples of how to run a conference, since this was the first time any of us were organizing and running a conference. And so you may see many similarities between HotStorage and SysStore, and that is because of the help they gave us.
Thank you for submitting. Thank you, researchers, for submitting all your works, and thank you for attending.
And finally, we just want to briefly discuss the logistics for today and tomorrow. So you can join through Zoom or YouTube. All of the talks are pre-recorded, and so they'll be played. But then the keynotes and panels will be live presentations. And then, of course, the Q&A will be live. So for every paper, at least one author will be present and within the panel. And so we'll be answering live questions. So we request that you please post your questions to Slack. Our session chairs will be monitoring the Slack channels. And so as an example, you'll see Slack channels that are labeled such as D1 S1 Flash, that stands for Day 1 Session 1 Flash session. And so you can post your questions there. There's a thread per paper. And then the session chairs will present most of the questions that are from in Slack to the authors live. And then, of course, the authors are encouraged to continue the discussion through Slack during the conference and beyond that. And that ends our opening presentation. We'll be moving into our keynote in a moment.
All right, so let's start the keynote session. We have an excellent keynote speaker, Dr. Sang-Yan Cho from Samsung. Before moving on, let me introduce the brief biography of Dr. Sang-Yan Cho. Dr. Sang-Yan Cho is a senior VP of Storage Systems Division from Memory Business of Samsung Electronics. He received the BS degree from Computer Engineering from Seoul National University in 1994, and the PhD degree from Computer Science from the University of Minnesota in 2002. In 1999, he joined the System LSI business of the Samsung Electronics and contributed to the development of Samsung's flagship embedded processor core family, CARM RISC. And in year 2004, he joined the faculty of the Computer Science Department of University of Pittsburgh. He joined Samsung's memory business in 2012, where he is currently overseeing enterprise solid-state drive development programs. His technical interests are in the area of computer architecture and systems with particular focus on performance, power, and reliability of data center storage systems. He is a fellow of IEEE. Sang-Yan, you can see my screen and go ahead and start the speech.
Okay, so do you see my slide?
Yes, yes.
Okay, good. So Professor Wan, thank you very much for your kind introduction. Hello, everyone. Good morning, good afternoon, good evening. I'm very glad to be here talking to you. First of all, I saw the title of the best paper awardees. And at Samsung, we will make sure that our 3D NAND flash memory will never fail on you, okay? Okay, let me begin. So today, I'm going to talk about SSDs, obviously. I'm doing SSD development programs at Samsung, and we look at many different ideas that will benefit the users of our SSDs. Before doing that, let me briefly touch upon the history. So this is the chart that captures the areal density trend of the rotating media, right? So today's data center in the past few decades, the data center expansion and advances are largely fueled by the continued innovation in areal density improvement. Now, if you look at the very first hard drive that's introduced by the IBM in 1956, whose capacity was 3.75 megabytes, and using the traditional cylinder head sector address, CHS method, all the way to the modern data center high capacity drives from different vendors, whose capacities are like 16 terabyte to 18 terabytes. And if you look at the 55-year history, so the annual areal density growth rate is in excess of 40%. At one point, starting from year 1995, this growth rate was as high as over 80%, right? And then more recently, from 2001, the CAGR comes down to 37%. And even more recently, in the past decade or so, the CAGR comes down further to 10%. If you look at the progress in the NAND flash domain, in the past 20 years or so, we are seeing a similarly exponential growth in the areal density. So the CAGR is in excess of 80%. That's an amazing accomplishment by many companies and engineers and scientists and researchers. If you look at the recent picture here, we've already got a terabit device. So a single die gives you a terabit capacity, right? And the recent focus has been on developing 4 bits per cell NAND flash memory technologies. Right now, the mainstream media is 3-bit cell, but this trend basically shows that in the future, we'll see more and more 4 bits per cell technologies in the actual products. So assuming that those papers published at ISSCC will be very similar to the products in 1 to 3 years, these are the technologies that you are using in your most recent SSD purchases, right? So if you look at the TLC, each chip carries 512 gigabits with the 45 microsecond read latency and 82 megabytes per second program throughput. So if you are talking about multi-terabyte SSDs, you are packing hundreds of these chips. So if you look at the 82 megabyte throughput with, say, 128 dies, you can easily saturate the PCI bandwidth that you are using. So that's the power of parallel data access using NAND flash memory technologies. So this is somewhat personal experience at Samsung. About 5 years ago, we are working very hard on new SSD products for enterprise data centers. And we were looking at introducing VNAND for the first time in history to the enterprise SSDs. And not only that, we were working on introducing TLC, the 3 bits per cell technology with the product. So at that time, the status quo was to utilize SLC, the single level cell, or something called enterprise MLC technologies. This is because of the stringent performance requirements as well as reliability requirements. And nobody was thinking about using VNAND or TLC in enterprise SS domain. But by doing so, we were able to substantially reduce the cost of the SSD in this domain, which dramatically changed the landscape of all-flash storage systems and all-flash data centers. Moving on. So if you compare these two devices, performance HDDs at the time and the very first 3D VNAND TLC SSDs. So in terms of performance, of course, the performance was the key. We had the very compelling megabytes per second numbers, IOPS per dollar, IOPS per gigabyte numbers. But equally important was the density offerings. So if you look at HDDs, you were basically given 300 gigabyte hard drives or 600 gigabytes. However, in the case of SSDs, we were able to offer half terabyte all the way to 16 terabyte devices, giving a lot of different system level choices for the different systems. That was quite important at the time for different system builders. And also important was the AFR, that's the annualized failure rate, and SSDs were much better than mechanical hard drives in terms of that as well. So combining all these benefits, performance, the density choices, and AFR advantages, basically made all those major server vendors, especially server vendors, jump into grabbing this device. And that was quite a moment for SSD history and technology advances of enterprise storage systems. And let me talk a little bit about the 16 terabyte product. In 2017, we introduced this product called PM1633A, 16 terabyte product, mass produced in that year. It's arguably the world's highest capacity drive at that point of time, and that includes the hard drives, okay? So 16 terabyte drive was the very first one in history in 2017 that's SSD in 2.5-inch form factor. So we had to introduce a new architecture to realize this. It's a scale-out architecture within the SSD. So we had the main controller and 8 subcontrollers, each having its own DRAM capacity and a set of NAND flash chips. So this was the very first time to also utilize the LPDDR4 DRAM. That was unusual because this is typically for your mobile phones, not for enterprise products. But we brought in this technology to save the power consumption of this device. So looking at how we packaged this hardware, right? So we put a scale-out controller here with 4 pieces of DRAM chips, all in the single package. So we have 8 of these things. And then NAND flash package is another engineering marvel. We stacked up 16 256 gigabit VNAND chips. Of course, each VNAND chip has many layers of 3-bit NAND cells. So putting all this together, this drive was 135 gram in weight, and it was more valuable than the pure gold of the same weight. Let me jump into the first topic of my talk. So in today's big data applications, in traditional systems, basically you grab all the data from the storage server, send them over to the processing server, and perform certain processing. And in many cases, the CPUs were suboptimal for these algorithms because you're dealing with data, not complex algorithms that require a lot of instructions for computing. Was much simpler job to scan through data, for example. So for such workloads, it makes more sense to move the computation from the processing server to the storage server to save the bandwidth of the interface network, and also by some specialized hardware, you could accelerate the data processing. So this approach is typically termed near data processing. You process your data by the data, not in the processor, right? And the idea is everywhere. If you look at this example of Oracle Exadata appliance, it has a database server connected to flash storage servers through the internal network. And clearly, the bandwidth here, you have the bandwidth bottleneck between the flash storage servers and database servers. And when certain conditions are met, the database server can issue a command to the flash storage servers, which can perform certain actions on behalf of the database server, like smart scan, reducing the result. So the small amount of data will be transferred to the database server. Similarly, in a more recent Amazon Aqua architecture, this advanced query acceleration architecture, they introduced the Aqua nodes, where they have their own analytics acceleration processor with SSDs in the Aqua layer, such that computing is actually done in this layer, not in the traditional compute nodes. We had similar ideas within the SSDs. We wanted to really push the compute to the far end. And this diagram captures a typical SSD hardware architecture where we have embedded CPUs, on-chip SRAM and DRAM, and a number of flash memory controllers connected to flash memory channels. So we focused on the flash memory controllers because this is directly related with the amount of bandwidth that you can leverage within the SSDs. So as you add more flash memory channels, you are adding more compute to match that. And in our early work, we wanted to theoretically prove that this makes sense. So we looked at different process architectures within the SSDs, a general purpose embedded processor, or more special purpose-built, power-efficient acceleration architecture that resembles a coarse-grained, reconfigurable architecture. We called it a stream processor. Okay, so using this setup, we studied how the near data processing helps. So these are the first set of results that I want to share with you. These can be all found in our publication at ICS 2013. Here, I'm showing 4 workloads. For each workload, each chart shows the number of flash memory channels. That's the bandwidth available to your system. It could be a single SSD, multiple SSDs, doesn't matter. Here, the unit is the number of flash memory channels. The y-axis is the data processing rate, so the higher, the better. The flat lines capture the performance of traditional method, traditional host-based processing. Typically, the performance is bottlenecked by the host and SSD interface, or the suboptimal performance of CPUs. On the other hand, with the near data processing framework, as you add bandwidth to the SSDs, you can scale your performance quite linearly, right? And you have similar results for all these 4 workloads. But in the case of string match, a general purpose processing within the SSD running at higher clock frequency was more performant than running the algorithm through the specialized hardware. Whereas if you look at the simple algorithm like scan in the last one, acceleration gives you a high performance boost as compared to the embedded processor configuration. If you compare the throughput efficiency of the CPUs and the specialized per flash memory channel acceleration, we have a good understanding of which is better choice in terms of the overall system resource usage. Here, I'm showing two charts. The left one with the limited host I/O bandwidth. The right chart, it has an ample bandwidth between host and I/O, the SSDs. So x-axis is the number of host CPUs, y-axis is the number of flash memory channels coupled with the processors, right? Per channel processors. And each line captures the ISO performance points between these two different resources. For example, if you have 12 CPU cores, your k-means algorithm will perform identically if you have 24 flash memory channels. So the fact that we have lines all fit into these charts show that actually CPUs are not that throughput efficient, especially under constrained host I/O bandwidth, the left chart, right? And also shown is the effectiveness of accelerator per flash memory channel as compared to general embedded processors per channel. This is intuitive, but at the same time surprising. The energy efficiency wise, the in-storage computing or near data processing gives you a lot of benefits. So in the case of host processing, you spend energy in host CPU, main memory, DRAM, chipset, and I/O. Basically, you have to move your data, whole data from SSDs to the main memory of the host system for the CPUs through different components in the platform like chipsets and I/O links. That's why the energy is spent moving around the data. That's inefficient. And in these configurations and under these workloads, we were able to observe the energy savings of anywhere between 5x to 20x. So encouraged by these theoretical results, we actually went on to develop a real product like prototype here. So this is actually a real product, but we work with the hardware designers to implement a simple pattern matcher in the flash memory channel, just as we studied in our theoretical research work. And the focus was on implementing that in the controller, and the controller was ready in time. And we were developing software systems for programmers. So we chose the C++ language for programming this device, right? And we allow the user to dynamically load the user binary onto this SSD. And we also wanted to seamlessly support hardware acceleration. That's really important according to our theoretical study. So this system came out after this work. So we have the software system running on the host, our library, and our NVMe driver. And we have a runtime on a specialized runtime for the user binaries running on the SSD. We called our system Biscuit, and this work was published in ISCA 2016. So the Biscuit system, Biscuit programming model. Biscuit is a programming model and its implementation in our hardware. Basically, Biscuit refers to our system. We were inspired by the data flow model. We split the work between different tasks, and they are connected with each other. And data flow between tasks as they become ready, right? And based on this model, it was quite straightforward and intuitive to write a map-reduced type of a style of application running in the SSD. So our software allowed the tasks to be dynamically loaded into SSDs and spawned and talk to each other, also connected to the host side program. So host side program controls the execution of those tasks running in the SSDs. And we provided the abstract control methods like file system like interface for the tasks running in the SSDs. And also the host side tasks and the SSD side tasks could work in the same data flow model. So this slide captures our reality check. So earlier I was saying that the bandwidth available within the SSD could be really large, right? So if you look at this chart, the lowest line here, it captures the actual bandwidth you can get outside the SSD at the host system, and the uppermost line captures the bandwidth that we can tap within the SSD. So there was a 30% gap that we could utilize in this particular product. And also we measure the latency to access a small chunk of data within the SSD and outside the SSD. And at the zero load in the host system, the latency gap was only 10%. But as we add more and more loads, more threads in the host system, which is typically the case, right? You keep your servers busy. The latency of accessing I/O from the host system gets longer and longer. Whereas if you are running your task within the SSD, you are not affected by the actual CPU load in the server system. So this was quite a resilient latency number. So the gap is widened to over 20% in this experiment. So the real thing is the application level study. So we built a system called YourSQL. Of course, we derived YourSQL from MySQL. We had a few important design considerations here. We needed to partition the job between the host and the SSD. And SSD resources, even though we included quite powerful, yes, simple yet quite powerful pattern matcher within the SSD controller, but the embedded processors are not really special. They are not high performance. They are low power processor cores. So you cannot offload anything you want onto the SSD. You need to be careful about what to offload and what not to. And we need to define the interface between host and ISC tasks. We optimized query planner in the original MySQL, right? And we reorganized the data paths from the upper level software all the way down to the SSDs. So we implemented a few new modules, and we modified 2 key modules in the query engine, and we added a few tasks to the SSDs. I'll skip a lot of details because they are in the paper we published at VLDB 2016. We chose 22 TPC-H queries to run, and we were able to leverage the hardware for 8 queries. I already mentioned that our pattern matcher was a very simple design research prototype, and many of these queries actually require more complex hardware operations like multiple matcher, some regular expression like matching, and also range checking kind of matching capabilities. If we have such hardware support, then we'll be able to leverage that hardware for, I think, more than 2/3 of these queries for sizable gains, right? So if you focus on the top five queries that benefited from our approach, the gain was as high as 167x for the top 1 query, the query number 14. And the average, the geometric mean of the gains for the top 5 queries was as high as 15x. Okay. Equally impressive is the energy consumption. Just like we predicted with our theoretical study, we were seeing 24x lower energy primarily because you are executing your queries so fast, you don't have to consume energy continuously. So we were able to gain a lot in terms of energy as well. Okay. So that was kind of a theoretical research work to prototype work on a real product. And actually now we have a real product called Samsung Smart SSD. Well, this is a real product that's being produced now, right? Inside the package, we have actually three relatively independent components. The first is clearly the full-fledged SSD, right? And then we have an accelerator outside SSD. This is outside SSD, not like our previous work, right? It's actually an FPGA with its own DRAM. And then we have a PCIe switch that connects these two components to the host and with each other. Because these two components are on the same PCI address space, they can see each other, they can talk to each other without going through the host DRAM and host CPU. So this gives us a good opportunity to implement those near data processing ideas all inside this smart SSD package. So this use case is a video transcoding. So now we are communicating with Zoom, right? So video transcoding is a very important workload in many applications like Zoom. Here, the x-axis is the number of SSDs we plug into a single server. Y-axis, the first Y-axis is the throughput, the number of frames per second that you can process transcode. And here, the second Y-axis is the CPU utilization. So now you add 3 SSDs in a conventional system, the CPU utilization is basically saturated, and the performance is basically flat. You cannot scale performance even if you are adding more and more I/O bandwidth, right? However, if you implement this transcoding algorithm in the FPGA accelerator, as you add your SSDs on and on and on, you can continuously scale the performance all the way up to 24 drives. Your CPU utilization starts at a very low point and gradually goes up as CPUs get work to do to handle jobs for transcoding mostly done by the smart SSDs. So this is a quite powerful use case where you can increase the total capacity of your server without adding CPUs, but by adding SSDs. So this is a very realistic application level use case study. Okay, moving forward, right? This diagram captures the futuristic platform, especially given that the computational storage concept is being standardized at different standard bodies, right? So it's a heterogeneous platform where you have CPU, GPU, DPU, and a number of computational storage devices. So there are many technical questions that you may ask, and there are research problems here as well. For example, what target applications will benefit from a heterogeneous platform like this? A database, AI, and scientific computing applications are obvious targets, but there will be more. And what are those applications? And how do we program our applications to best utilize these heterogeneous resources, including computational storage devices? And how do we coordinate and maximize the use of all the platform resources, right? And in order to access the computational storage devices, what will be the best and right data access mode? Through traditional block, or key value or object interface, or even memory-like load store instructions. What about physical interconnect? We could use PCIe, but CXL is upcoming. And NVLink with NVIDIA GPUs, right? or even Ethernet or InfiniBand type of a fabric to connect to computational storage devices. So these are the system level questions that are quite interesting to me and to many of you, I believe. And if you are given many computational storage devices, in our previous example, I was showing a configuration where we have 24 such devices, right? How do we partition the data among those drives, and how do we utilize the computational resources on those drives? And that's, again, a legitimate question to ask. Okay, now I'm moving on to the next topic. That's to get the most from the storage media. So SSDs have been successful because SSDs are just like hard drives, talking to the host through the generic block layer or LBA addressing method, right? That paved the road for SSDs to be easily adopted in different systems. However, we all understand that under the hood, the operating principles and mechanisms on these media are totally different. In the case of hard drives, to get your data, you need to move the arm, wait, and access the target sector. On the other hand, in the case of SSDs, I was talking about the modern NAND flash chips, right? 512 gigabits, 45 microsecond latency, 82 megabyte program bandwidth, right? It's a basically digital device. You have many of those things. So sheer performance-wise, it's you have sheer performance out of those aggregate parallel NAND chip units, right? You address one of those and you read. You address one of those, you write, and you address one of those and erase a chunk of space. And that's a big difference. The NAND flash does not allow you to update data in place. So this causes a lot of artifacts of the SSD performance behavior that was an important topic for many of those storage server designers, service designers, if you will, in 2014, 15, 16. So this is an example of how the performance of SSD changes over time. So here the x-axis is the time, y-axis is the Cassandra update throughput. So starting from a fresh, empty SSD device, and starting from the 100% of the throughput, you see that after a certain point of time, the performance drops rather dramatically. And many of the early users didn't understand why this happens, right? SSD is supposed to be really high performance. The performance should be consistent because it's an all digital, no moving arm, should be super fast all the time. But this is what happened, right? And in our paper that appeared at HotStorage, this venue in 2014, we showed that this performance drop is a very close reflection of what's going on inside the SSD. So the red line captures the SSD internal operations to bookkeep the space. I was talking about the not being able to update in place, so we have to garbage collect. Typically, after use for a certain time, SSD media are fragmented, and when you perform garbage collection, it's a high overhead data copy operations followed by erase operation, right? That's why these lines look so similar and are reflections, right? So how do we solve this problem? So in that paper, we were proposing a new interface called multi-stream. It's an addition to the traditional LBA interface, right? And we gave the ability to the host to specify the stream ID to each data being written to the SSD. The stream is a unit of data, a fixed size, that aligns very nicely to the flash memory, underlying flash memory media geometry. So with the simple stream ID information, SSD tried its best to organize data based on the stream ID, right? So that when the data are in no use, we can erase the data and we can very nicely erase the physically related chunk space in the NAND flash media so that we don't have to perform expensive garbage collection operations. And we published this work in 2014 at HotStorage, and I'm humbled to see that the idea was standardized in both SAS and NVMe by 2017, within 3 years. And Linux support started in 2017 as well. And in the meantime, we prepared a real product, and that product debuted in 2016 and 17 timeframe in enterprise storage systems and hyperscale data centers. So what's the net effect? This is the same diagram, same chart that I showed you in the previous slide. With the multi-stream SSD technique, you can sustain the high performance of SSD, and you get the most out of the underlying media this way. So good thing about this approach is that this is a very simple, intuitive model. And as I said, it's an additive model, implying that this SSD is just like normal SSD. You can use it without multi-stream capabilities. It's just like your normal SSD. But if you decide to use this multi-stream capability, what you need to do is just attach the stream ID to the data being written. Okay, so easy to use, easy to adapt, no risk. And the model, the proposed model, is concrete enough to predict the effects, as I showed you, captured in this chart, right? However, in some sense, the model is still abstract. The host can't precisely control the data placement on specific NAND flash media, if you will. So there was an approach called open channel SSD. This is an extreme direction to fully expose all the geometry information of the NAND flash media. So all the responsibilities now go to the host software, host layer, to manage properly the media. So basically, this approach eliminates a good portion of FTL that used to run in the SSD, so that FTL now runs on the host system, and the host system has the full control over data placement and access schedule to individual media units. So that gives you the feeling of being very powerful, right? You can do anything you want on NAND flash media. Just give me the NAND flash media and reasonable controller that has a good data path from the NAND flash media all the way to the PCIe of my host server. I can do everything that I want for the best end result, right? Theoretically, yes, that's right. The host has a complete control. So basically, there's no LBA, okay? LBA is a logical block address thing. There's no such thing here. It's all NAND flash block, NAND flash chips, NAND flash plane, NAND flash page. All these NAND geometries with peculiar sizes are exposed to the host software, right? Yes, there are opportunities to optimize the host level software across the layers, including FTL, file system, OS block layer, even device driver, applications. You can do anything, right? Theoretically. But there's a serious drawback to this approach from the beginning. The NAND flash is not as easy as you might imagine. If you can properly program and utilize today's hard disk drive right? If somehow hard disk drive now expose all the geometries to you, can you utilize the hard drive's platter and head mechanics better than the hard drive vendors who created the products? NAND flash is no less complex today, and there are lots of different characteristics and idiosyncrasies there to fully utilize the capabilities of the NAND flash memory, performance, and reliability. So those aspects were underestimated by the open channel proposals, right? So the question is, do you want to go back to CHS addressing method, just like the hard drives, very first hard drive in 1956 did, right? Giving up the LBA. So I saw some instances of open channel SSD implementations and deployment in certain scale, but I see very rough roads ahead for open channel SSD approach because of this particular issues that I mentioned. So you have perfect system you built in 3 years. And while you are doing that, your competitors have already switched it to the next generation NAND flash SSDs from Samsung, and they were much happier and enjoy all the benefits of newer NAND flash and SSD controllers and so on and so forth. So this is a tough road ahead. And this is the newest interface that is becoming, has a good potential to become popular. Zone namespace is a standard in NVMe. So SSD LBA space, LBA is there. SSD LBA space is split into multiple zones, right? And each zone is a write unit. You need to sequentially write onto those zones for each zone, right? And it's very similar. You are reminded of this shingled magnetic recording hard drives, right? They have zones, and you need to sequentially write those zones. Just like that, zone namespace, SSDs, you have many zones. You pick up the zones that you want to write to, you sequentially write, you are done, you are good. You can read from the zones that you've written. And with that simple concept and interface ideas, you have the ability to place your data onto physically related or physically unrelated portions of your the underlying media. So achieving the goal of the original multi-stream approach aimed, right? You want to eliminate any internal operations that move around the data within the SSD. So the idea is zones, once you are written, that's immutable. You perform host level data rearrangement or garbage collection up there at the zone level, right? But SSDs, from the viewpoint of SSDs, zones are units written, done, erased at the same time. So it's very easy to manage within the SSD. So host has a control over data placement on NAND flash media. That's good. That's what this interface is about. And the important thing, unlike the open channel SSDs, the complicated media management all resides within the SSD. That's important. That's why I believe zone namespace has a better future than open channel SSDs. But just like the open channel SSDs, for you to utilize that zone namespace SSDs, your host software must be aware of these zones. Fortunately, if you've been working on SMR, you are almost there. You can leverage what you've been doing, right? One caveat here is even though this is a standard, you understand all the parameters, what they mean, but there are certain design trade-offs that you may not be able to grasp at the beginning. For example, you have a 1 terabyte zone namespace drive. You may have 1,000 zones with certain size, or you may have million zones with smaller size. Which configuration do you prefer? Both are ZNS drives, both are zone namespace drives. Which do you prefer? Small zone, small and many zones, or large and fewer zones? That's not a simple question. And that will affect how you schedule your programming and writing operations onto the SSDs from a host, and how these are handled within the SSDs. It has a lot of performance ramifications. Okay. Moving forward, when in fact, just last month, my team finished the development of the commercial ZNS SSDs. And ZNS SSDs are available from multiple vendors, and especially for large storage systems, this is quite amenable. It's a good fit because it has very concrete interface. You can control the media much better than conventional SSDs. And moving forward, this could be a very good fit for many bit cell technologies. When I say many bit, it's 4 bits per cell or even 5 bits per cell, where we expect that the endurance available to those technologies will be smaller than what we have today. And software availability and readiness is pose a lot of challenges for users, right? And that's one of the reasons why we are working also hard on open source projects like XNVMe, providing you with the APIs and libraries to more easily utilize ZNS SSDs on Linux, BSD, or on SPDK libraries. And I expect that more end-to-end software building and design trade-off studies to be really valuable in the future, because we have a limited understanding at this point about those subtle interactions between parameters of the SSDs and host systems. One more slide on the next generation SSD. The multi-tenancy becomes a fashion. It's important to support multi-tenancy from the viewpoint of storage devices as well. And for one, SSDs are now very powerful, a large capacity, right? 16 terabyte, 32 terabyte drives are available, and really high performance drives are there. Now, you don't need that much of performance and capacity for a single virtual machine. So you want to map multiple virtual machines to a single such large capacity, high performance SSDs, but you want to create an illusion that each and every virtual machine has its own isolated a dedicated SSD, right? To do so, we need the capability to partition the capacity and control the data placement, right? And also to provide adequate performance at the low power. Hardware acceleration of common I/O operations and key functions will become more and more important. Per partition or per VM bandwidth allocation, performance QoS control, schedule guarantee, and per partition housekeeping will be required, right? In order to create the illusion that the partition given to each virtual machine is a completely isolated SSD. Likewise, increasingly more concerns are on security guarantees on multi-tenancy, and SSDs will evolve into providing certain mechanisms for the host system to control the SSD in such a way to provide the hardware level isolation per virtual machine, and also very fine-grained encryption support so that different virtual machines are encrypting in different ways, right? These are being prepared and being standardized, and we expect that future products will have these capabilities. Now, I have a couple slides, a few slides. It's a bonus track. This is something that I felt really interesting to share with you. SSDs provide you with a lot of debug purpose telemetry data, and they actually disclose quite interesting and intuitive, insightful data for you if you are dealing with the large installations of servers. For example, here I'm showing the data for 5 different data centers, and x-axis is a temperature that SSDs are seeing, SSDs have temperature sensors, and temperature sensors report the temperature, and those temperature readings are in the telemetry data. And the y-axis is the SSD count, so that's population. So if you look at the data center number 3, they have a really good control over the temperature of the servers, right? It's a very thin. But if you look at the data center number 4, they are more loose, more relaxed control of temperature. If you look at data center 1 and data center 5, you will see a long tail. So there are SSDs in the hot servers, right? So it's very interesting for me to see how different environments that our SSDs are experiencing in the real field. This chart captures the temperature of the SSDs in different servers and different slots. So y-axis is the slots. So even within the same server, you will see the gradient, different temperature ranges that SSDs are seeing here, right? And if you look at horizontally, servers in a certain racks or location within the data center have advantage in cooling, whereas other racks or other servers are, not getting the, as cool air like the first rack. So that was also interesting. There's some asymmetry there within the data center. And we actually found some problems here. Again, x-axis is a server ID and type, and y-axis is the temperature-related warnings logged in the SSDs. So for certain types of servers and certain server population, we were seeing particularly many warnings. So we have 2 such server types, right? So we looked deeper into what's going on. X-axis is a time series, it's a date. Y-axis is a temperature, and we are showing with each line the SSD temperature. And as you can see, there are many red lines up there. These are the outliers that are captured in the previous chart. So we looked further, and we identified that these drives are actually on a particular slot in particular servers. And that led to the detection of a software configuration mistake in the server systems. So these are the temperature of those drives, right? So at a certain point, they fixed this bug. So they turned on the fan within the server, and the temperature of these drives all went down very nicely, all at the same time. And the workload SSDs are seeing are also quite different. X-axis is a different servers, so y-axis is a slot ID. The colors capture the amount of writes they received over the lifetime of the drives. We are talking about the thousands of drives being installed at the same time 3 years ago, okay? So this was quite surprising to me. X-axis, amount of endurance usage, y-axis is SSD population. So I'm seeing 2 different groups. The first group on the left have received much less write traffic over the lifetime than the group on the right-hand side. So as system scientists and researchers and engineers, we don't like this kind of picture. We want a much nicer normal distribution curve, right? So seemingly, the services that are utilizing these SSDs are statically allocated in 3 years, and boom, this is what happened. Okay, so let me finish. Data centers are, advancing at an astounding rate, continues to do that. SSDs are also making good progress into higher performance, a better control over media usage, and also even near data processing. And they are interacting with each other. And I expect some nice system changes to leverage the realized ideas around SSDs, like near data processing, media aware utilization of the SSDs like CNS, and also hardware level isolation support for multi-tenancy. So if you're looking for some interesting problems in the domain, cross-cutting the SSDs and host systems, I mean, end-to-end software building efforts and novel data compute mapping and coordination in the context of ZNS, multi-tenancy, near data processing platforms will be quite interesting and will be very valuable. With that, I'd like to conclude, and thank you very much for your listening to me. Thank you.
Well, that's a very exciting talk. Thank you very much. We have 5 minutes for question and answer. And there I saw some questions on the Slack channel. Let me reread the questions. This is the question from Luna Zhu. What is your opinion on the selection of processor unit in a computational SSD and how to make it generic if you are not able to manufacture one of the smart SSD for each specific use case?
Right, that's an excellent question, and that's also very practical and relevant. So when we were doing theoretical study, I was saying that we wanted to push the compute to the farthest point that just before the NAND flash channel, right? But we realized that from the viewpoint of coordination and programming, that's really challenging because you need to control the data mapping even at the channel level. That was not really feasible. So the right computation, right point for putting computing is at least above the channels and before the host CPU. So that's how our product idea came out with the FPGA coupled with the real complete SSDs. So I still believe that that's the right point to put the compute. And in order to utilize, many choices in SSDs, we could have a FPGA architecture that can plug into any kind of SSDs, or even coprocessor, computational storage processors that could hire a few SSDs below and sit between the host CPU and those SSDs, just like Amazon implemented their analytics acceleration.
All right, thanks for the answer. Another question from Jeff Cunning at Harvard College is that this computational storage device has a CPU, memory, and persistent storage and network connection. So this is just a computer itself. So isn't this just a case of recognizing that interconnect between the CPU and the storage is inadequate and redesigning the motherboard to solve the problem? Then what is left for the host to do?
Right. I think that's a really interesting question. I do wish that such computer systems would appear. As a SSD researcher and developer, we always think about how SSDs can contribute more to the overall systems. That's how computational storage concepts all come along, right? So by adding a right resource to the right point, the overall system balance and effectiveness go up. That's how we look at what we do. On the other hand, because of the concepts, today's computer architecture and systems concept, SSDs are SSDs. And it's a passive storage devices. And it's given instructions and it performs those instructions, right? Of course, it's a complete computer. Inside the SSD, we have a booting sequence and waking up all those processors. Like modern enterprise SSDs is a complete multi-core processor. I mean, the number of cores is now almost 10, 20 range. So it's a very powerful computing platform. And we need to continuously work on finding the best way to utilize those available resources inside the SSDs. But I don't have the right answer to how to make the CPUs slave to SSDs.
All right, thanks for the answer. We have running out of time and there's lots of questions left in the Slack channel. I would pick one questions and close this session. The Somali Chatterjee from Purdue University has asked a question that SSD technology advances a far faster pace than the software vendors can catch up.
Right.
So how do the software vendors make up the difference between the technology advancement between hardware and software? By the time they optimize the software for the SSD, the new SSD is going to come up. Then do they waste their effort for optimization for this new SSD hardware, or how they catch up the speed of the hardware advancement for the software vendors?
Right. I think that's a really great question that everyone in this conference might want to think deeply, right? I do wish that as we introduce new devices, the software ecosystem is just ready to be able to utilize available hardware resources in a perfect way. But clearly, that was not the case. For example, in the case of a multi-stream SSD, it took a good 1 to 2 years before the host software became ready. ZNS is the same. It's almost like 2 years effort, even if we have a clear productization target. Open channel, it could be a never-ending story, right? As I already mentioned in the talk. So I think the best we could do, put the ideas in the standard, especially in this domain, SSD and host system co-optimization, standardization effort, publications, exchange of ideas, and then they have to start at the same time. Typically, from ideas to controller to SSD products, depending on the difficulties, is anywhere between 2 to 4 years. So host system should be ready in that time frame. If they abide by this interface concepts and interact in between during those time period, maybe we could have a much better matched host software systems and SSD products in the future.
So the plan ahead is the only way to solve this problem. Okay, all right. So there is many questions unanswered in the Slack channel. So Dr. Cho, please read the questions and write the answers at the Slack channel of the keynote speech. And again, thank you very much for an exciting talk. And everybody, we'll have a break for the sessions and we'll resume in 8:15 Eastern Time. Thank you very much.
Thank you very much.
Okay.
Hello, welcome everyone to our first session on the flash storage. Me, Janki Bhimani from Florida International University, along with Jian Huang from UIUC. We are going to chair this session. Before we begin with the talks of the session, we are just a general guidelines that we would encourage everyone to get their questions on the Slack channel right when the talk is going on so that we can get to as many questions as we can during as a live Q&A. And a guideline to all our speakers of today for Q&A, please stop your audio and video while the talk is going on, but on them when you come live for Q&A. That would help us throughout the session. With that, Jian, do you have anything else to begin?
Yes, I think this will be a very exciting session. So we are going to start from the 3D NAND flash and then to QVIO SSD and then to stream SSD and then to zone SSD. So we cover lots of exciting SSD devices. So.
Okay, so then let's welcome our first speaker, Quan Huang. She is a postdoc at City University of Hong Kong. Her research interest lies in reliable and high-performance memory and storage system. We have seen her previous work published in the top conferences and journals like Fast, Micro, DAC, and Transaction on Computers. Also congratulate to the authors for the Best Paper Award. Let's please play the video.
Hi, my name is Chang Li. I'm from City University of Hong Kong. In this video, I will introduce our work, how the common retention acceleration method of 3D NAND flash memory goes wrong. I will first introduce the flash retention acceleration method that is widely applied. And then through a one-year retention evaluation, I will then present how this method is not correct on 3D NAND flash chips. Next, I will present the real long retention errors and some discussions, followed by the conclusions of this work. The number of applications is greatly increased in these years. This trend causes high I/O pressure on the storage systems, in our case, SSD devices. Current 3D flash memory-based SSD has been evolved from 2D to 3D to provide higher storage density and better performance. To provide even higher storage density, the solution is increasing the number of vertical layers of 3D NAND flash memories. NAND flash memory stores charge in flash cells and represents data based on the threshold voltage of cells as shown in this example. Several types of error sources will impact its reliability, such as program recycling and retention time. And retention errors is one of the most important flash errors, which are caused by charge leakage over retention time. To guarantee the reliability of stored data, the flash controller provides error correction codes that are strong enough for the rapid error rate after a long retention age, for example, 1 year. However, it is time-consuming to observe the retention errors over a year or even longer. In practice, high temperatures are applied to accelerate retention effects because high temperatures increase the mobility of electrons. Arrhenius law is widely applied through baking flash chips at a high temperature to obtain the equivalent retention effects to that of a low temperature. Based on the law, we can calculate the baking hours if we want to know the retention effects at 25 degrees for 1 year. For example, as shown in the table, we need to bake at 60 degrees for 97 something degree hours or 100 degrees for 1.6 hours. We conduct evaluations on real 3D NAND flash chips to study the retention acceleration method. This is our evaluation platform, and 4 3D flash chips are evaluated. The experiments were conducted over multiple temperatures. For 1 year retention at room temperature, flash chips are placed in the office with air condition and the temperature is set at 25 degrees. For high temperatures, we calculated the baking hours according to the law as shown in the last slide. Through the evaluations, we will present 5 new findings that are contrary to our common beliefs. Our first new finding is that the errors through baking with high temperatures significantly underestimate the real long retention errors. The upper blue line shows the repeat error rate at 25 degrees for 1 year, which is the real long retention errors, and the other lines shows the errors through baking with high temperatures. We can see from these two figures, one charge trap flash, one floating gate flash, the real repeat error rates after 1 year retention time are much higher than those through baking with high temperatures, more than 20 times in some cases. Our second finding is that the difference between the real and estimated errors on 3D floating gate flash, this one is floating gate, is smaller than that of 3D charge trap flash. This is because the retention acceleration method is developed in the 2D flash generation, where most flash chips are based on the floating gate cells, while today's 3D NAND flash memories mainly adopt charge trap technology as the fundamental flash cells. The acceleration parameters and models that used to be adopted on 2D floating gate flash chips introduce less deviations on 3D floating gate flash than that of 3D charge trap flash. Our next finding is that the difference between the real and estimated retention errors changes with the number of program and release cycles. When the number of program and release cycle is small, for example, when the repeat error rate of high temperatures, these 4 bars are very similar to that of 25 degrees, the real retention errors. With the increasing of number of P cycles, the difference between 25 degree and high temperatures becomes larger. The reason is that during the lifetime, flash chips endure a large number of program erase cycles, and every program erase cycle will introduce high voltages, which introduce oxide degradation and flash cell damage. After enduring different numbers of P cycles, flash chips could present different retention characteristics. The above 3 findings are made regarding the overall errors. Then we discuss the errors introduced by different read voltages. We use TLC as an example. Each TLC stores 3 bits in the cells, and there are 7 read voltages to differentiate 8 voltage states. Errors could be introduced near every read voltage. For example, these 2 voltage states may overlap, thus V4 may introduce errors. To read an LSB page, 1 read voltage, that is V4, is applied, while 2 read voltages for CSB and 4 for MSB. According to existing work, we know that higher voltage states suffer more from retention errors because they have higher voltages. Thus, different pages will have different errors because they require different read voltages to read data. So our fourth finding is that the temperature affects the repeat error rate variations among read voltages as well as flash pages. As shown in this figure, at 25 degrees, the difference between low voltage states and high voltage states are very large, while at high temperatures, 80 degree, 100 degree, the difference is much smaller. And the variations among read voltages also affect the variations among pages, the lines in the figure, as reading each page requires one or several specific read voltages. For the QLC flash chip, there are 15 read voltages and 4 flash pages. The variations among them are also changed. They have very, very large variations among these 4 pages at 25 degrees, but the difference is much smaller when the temperatures are higher. Our last finding is that the temperature affects the Robbie error rate variations among word lines. The Robbie error rate of different word lines inside the same flash block. This is the word line index in a flash block. The Robbie error rate of different word lines presents significant variations, which come from the physics structure of 3D flash blocks. Such variation has been reported by previous studies and considered as constant. However, in this work, we found that such variation is not consistent, especially CSV and MSV page when the temperature is changed. For example, at 25 degrees, the MSV page of this word line has the highest Robbie error rate, while at 80 degree high temperatures, the CSV page of this word line has the highest Robbie error rate. Based on above findings, we can conclude that the error behaviors over a long retention time at low temperatures are very different from those through baking with high temperatures. As a result, we cannot achieve the equivalent error behaviors. Then, as current long retention errors are all estimated through baking with high temperatures, we first present the real retention errors of 3D flash chips over 1 year at room temperature, that is 25 degrees in our case. As printed earlier, the error rates introduced by higher read voltages are much higher, and the charge trap flash has much higher error rates than floating gate flash chips. Based on our evaluations, current retention calibration method is not correct, which will impact the flash reliability estimation as well as the reliability optimization method. Therefore, we need a new retention acceleration method for 3D NAND flash memory. Finally, the conclusion of this work. We conduct a 1-year retention evaluations on real 3D NAND flash chips, and we have studied that the real error behaviors at low temperatures are very different from that of through baking with high temperatures. And we provide the real long retention errors on 3D NAND flash chips. Thank you for watching this video. If you are interested, welcome to my session for online discussion.
Thanks, Kirk, for a very nice talk. You may please on your audio and video. Hi, nice to see you. So let me read there are a few questions on Slack. Let me read the upvoted one first. That's a question from Philip. It would be useful to have a way to accelerate aging. Do you have thoughts on new baking formula to replace the current formula since the current formula is inaccurate?
Thanks for your question. Yes, based on our evaluation, we already know that current formula cannot work on 3D flash chips. So our future work is actually based on the results, and we are working on that. We want to introduce a new method, and we we will present that result in future work. So currently,
Awesome.
the answer is no. We haven't developed the final model.
Awesome. So on the slides, we'll look forward to future publications from you and your team.
Yeah.
We have time for a few more questions. So the second question, I'll take that's from me. Do you observe any post-impact after the temperature becomes normal again?
Sorry.
So when you are exposing SSDs to higher temperatures, there is higher retention errors. But later when you remove the temperature and when it's back to the normal room temperature conditions, do you still observe any post-impact of that?
Yes. After baking with high temperatures, the retention errors will increase. That is definitely correct. But if you erase the flash block, for example, the block, you erase the block and program new data, the raw bit error will be decreased. This is called self-healing effects because during high temperatures, the charges in the flash cells will leak out. So it's like the program and erase effects is being reduced. So before erase, the error rate is high, but after erase and program, the raw bit error rate is reduced compared to baking before baking.
I see. So erasing helps. One more question. So most experiments show that the baking process leads to lower retention errors compared to real 1-year retention tests. So is it possible by adjusting the baking process with longer baking time so as to estimate the retention errors with lower errors?
Okay, thanks for your question. It is true that lower temperature with longer baking time will introduce smaller difference from the real 1-year retention errors. Based on our results, we already present that. But there still exists large difference, which could be larger than 1 order of magnitude. For example, 60 degrees is our lowest temperature in our experiments. If we continue to reduce the baking temperature, the baking time will be much longer. And in that case, the evaluation time would also be very long. And on the other hand, our evaluations also show that the error behaviors at lower temperatures are different from that of higher temperatures. So applying a lower baking temperature that is still different than the from the room temperature cannot solve this problem. So we still need a new retention acceleration method, and we are still working on that. So
interesting.
Yeah.
Well, thank you very much. Congratulations again to you and your team for the best paper. And looking forward to see the future works on this line in the future conferences. Thank you.
Thank you. Thanks.
With that, now let's welcome our second speaker, Donghyun Min. He's going to present on isolating namespace and performance in key-value SSDs for multi-tenant environment. He is a PhD candidate at Sogang University. His recent research interest includes flash-based storage systems and key-value SSDs. Please play the video.
Hi everyone, my name is Donghyun Min from Sogang University, South Korea, and advised by Professor Young-jae Kim. In this talk, I will present a multi-tenant key-value SSD with namespace and performance isolation. Key-value store is a type of NoSQL database which uses simple key and value interface. For example, LuxDB and LevelDB are host-side key-value store. On the other hand, key-value SSD runs storage engine of key value store inside the SSD. The application that uses a key value store performs right through a thick host IO stack, including indexing layer of storage engine and file system layer. But host file system's huge overhead has been reported, so to minimize this overhead, many studies have been trying to offload and implement storage engine of database inside SSD. And only with a thin host IO stack, key value SSD has a benefit in terms of performance. In particular, low-structured merge tree-based key value SSD have been proposed recently. So I'm going to first introduce the concept of LSM tree. LSM tree is a hierarchical structure that consists of mem table and SS table. If put requested with key K and value B from the host, will be appended to value log for persistence. Value log offset where B is stored are temporarily stored to mem table along with the key. When mem table is full, a set of key and value log offset are flushed to NAND flash memory in the form of SS table. In SS table, Bloom filter data structure is added for fast key search. And this SS table can be structured into multiple levels. If certain level SS table is full, then LSM tree chooses victim SS table of a next level that has overwrapped key range and reads them, and then they are merged into a new and big SS table one, and it is written to flash memory as a next level SS table. Then victim SS tables are invalidated. If get requested, key value search begins at mem table first. If not found, then key value search begins at SS table. If key is found, value is accessed by a log offset. Then value is retrieved. But there are two problems in current LSM tree-based key value SSD. First, current key value SSDs lack the multi-tenancy and namespace isolation support. Unlike single-tenant environment, the concurrent users are provided with their own dedicated server in a multi-tenant environment. Providing independent server to each user requires isolation in terms of security, privacy, and performance. These requirements can be met based on namespace isolation. The namespace isolation is to separate key value data of tenants into logical groups. However, current LSM tree-based key value SSDs do not support namespace isolation. Second, key value SSDs have difficulty in providing the promised read performance that storage device can provide. This is because multiple key value data of tenants are still managed by a global shared single LSM tree. Global shared single LSM tree hurt read performance. There are two reasons. First reason is most key value data is filled down to upper level of the LSM tree due to other key value tenants data. So most key value data will be indexed at upper level. Second reason is it must read Bloom filter from NAND flash memory several times. LSM tree search algorithm needs a lot of Bloom filter reads for key value data, which is indexed at upper level. So currently, per tenant read performance is limited. We confirmed this overhead in our motivation experiment using ILSM, which is a recent KVSSD. And we set up two read scenarios. First, when only tenant access key value data occupies our LSM tree. And second, when LSM tree is shared by tenant access and wise their own key value data at the same time. In case one, 60% of tenant access key value data is retrieved within 2 milliseconds. But in case two, 40% of tenant-wise data is retrieved within 6 milliseconds. The first reason is 67% of tenant access key value data are fed down to the next level of index. And second, the number of Bloom filter rows are increased by 77%. Therefore, we set up these design goals for multi-tenant key value SSD. First, it supports namespace isolation, and it minimizes the read performance overhead. To this end, we propose ISO key value SSD satisfying these two goals. This shows overall architecture design of ISO key value SSD. First, this namespace information is transferred from the host and stored at mem table and SS table along with the key. And ISO key value SSD allows key value data access only if the matching both key and namespace are satisfied. Next, ISO key value SSD employs the per namespace dedicated LSN3 design. In mem table and the lowest level L0 SS table, key value data of tenants are mixed and stored all together. On the other hand, in other level SS table, key value data is separately stored based on namespace. This approach was designed for two reasons. First, the performance degradation caused by both a shared mem table and L0 SS table is negligible because only few key value data are indexed as shared regions. And second, mem table provisioning per namespace approach requires additional DRAM space. If the number of tenants increase, more DRAM capacity is required, which is not suitable to DRAM constrained key value SSD. The main effect of the per namespace LSN3 is that it prevents key value data from being indexed at upper level of the tree. So ISO key value SSD can control access based on users' namespace information and reduce key value data's access latency. This shows a namespace isolation mechanism that substantially segregates key value data into per namespace LSN3s. This mechanism runs with existing background compaction. It first reads L0 victim SS table. Then ISO key value SSD checks key range per namespace. In this example, there are 4 namespaces in victim SS table, so 4 key ranges are identified. Then ISO key value SSD read L1 victim SS table for merge. And during compaction process, it segregates key value data into independent SS table based on namespace. Then they are stored per namespace dedicated LSN3. Because this mechanism aligns with existing background compaction, it segregates key value data without huge overhead. We prototype ISO key value SSD on FPGA-based SSD platform. Using put and get synthetic workloads, we compare ISO key value SSD with the baseline. Left figure shows that ISO key value SSD outperforms the baseline in terms of get performance. Particularly when the number of the tenants is 8, ISO key value SSD shows 2.9 times higher get throughput than the baseline. Because ISO key value SSD reduce the depth of LSN3 as well as reduce the Bloom filter load during the key value data search. On the other hand, right figure shows that put performance of both systems are similar. To see the impact of per namespace LSN3, we measure CDF on which level of index of LSN3 is searched during get. In baseline left figure, as the number of tenants increased, the number of searches from the upper level index increased. For example, the percentage at which key value data is searched in L2 SS table is around 70%. This is due to a global shared LSM tree. On the other hand, in ISO key value SSD right figure, key value data search is completed with only indexing of mem table and L0 and L1 SS table, regardless of the number of tenants, because key value data from other namespaces are indexed to individual LSM trees. Also, we measure how many Bloom filter rolls are performed during GET, particularly when the number of the tenants is 8. ISO key value SSD result in 3.6 times fewer Bloom filter rolls than the baseline. We propose ISO key value SSD, which identifies the user's namespace information and manages the key value data using per namespace LSM tree design. ISO key value SSD not only provides strict view to each tenant, but achieves read performance benefit. Thank you.
Thank you, Dongyun. I see you're here. Nice to see you. It's a
Hello.
very interesting paper, I would say.
Thank you.
Let's take the questions on the Slack. So I see the most upvoted question is from Vasily from IBM Research. He's asking, how many tenants per KVSSD do you realistically envision?
It will depend on the performance resource that key-value SSD can provide. If we allow more tenants and there is little change in performance degradation, then I think it is meaningless to operate the tenants simultaneously. So now we in our experiment we just set up 2, 4, 6, 8 tenants, but current our key-value SSD framework does not provide any very big performance advantage. So we didn't check the performance degradation by increasing the number of tenants. But I think it is meaningless to operate the tenant concurrently if key-value SSD the performance resource of key-value SSD is not is limited.
Okay, so what you mean is we can go beyond 8 as well, and there is not much degradation, but only if required. Interesting. Okay, so then second question is from Ujib from KAIST. Is there any interference among the compactions in different LSM trees?
Among different LSM trees. Okay. I think there is a performance bottleneck on level 0 SS table because in our design, mem table and level 0 SS tables are used by multiple tenants. So if I agree, the concurrency. Yeah, but because that SS level 0 SS table is not isolated, so it can be shown to for bottleneck. But I think nevertheless the overhead of that bottleneck is not perceivable because the size of level 0 SS table is not that much. And second is if certain CPU core which in charge of background compaction if that background core is in charge of many number of compaction, then it could be the delay interference between them.
I see. Okay. Another question we have from Philip from Dell Technologies. In your experiment, was the total number of entries kept constant, or did the total number of entries increase with the number of tenants?
Yeah, we assumed each tenant issues 1 million key value IOs constantly. So, and we when we increase the number of tenants, then the IO issued by the tenants will be constantly increased.
Okay. We have a question from Jian from UIUC. Compared to traditional SSDs, does KV SSDs manage the data layout inside the SSD in a different way? For example, does it also stripe the data from the same namespace across multiple flash channels?
We didn't leverage the internal parallelism like data placement across the multiple channels, but it can be possible, I think. And the core difference of traditional SSDs and key value SSD is the redesigning of FTL for key interface. That's the core different design. And other feature can be extended like traditional SSD.
Okay. A question from Brian Kim from Syracuse University. Since the mem table / the level 0 SS table is shared, that can be a source of performance interference. What are your thoughts?
Yeah, that's what I mentioned earlier. I agree that if some concurrency control issue, so I agree that concurrency control should be supported. But this was beyond our scope. But I guess if key value SSDs and its infrastructure are ready to support the concurrency control, then bottleneck might happen in level 0 SS table because that is not isolated. Nevertheless, the overhead is not perceivable because the size of level 0 SS table is not pretty much. That is my thought.
All right. Well, so then everyone over here, exploring concurrency would be a next good research direction. A last question. Why the proposed system adopts the key value separated LSM tree, and what would be the problem when the key value suppression is not adopted?
Key value separation. Many prior key value SSD work have been adopted. The key value separation. The key value separation stores value separately to value log, not along with the key, and so it can reduce the size of LSM tree. Accordingly, when the compaction is triggered, the key value separated LSM tree does not need to read value itself. So we also taken this design for the same reason. Also we didn't take key value. If we didn't take key value separation, then level 0 to level 1 isolation mechanism has more overhead when reading SS table, because it should read large sized value if key values is not separated. So in this case, the overhead of isolation mechanism would be not negligible. That's why we adopted key value separation.
Awesome. Thank you very much, Dongjun. And very interesting talk as well as very interesting paper. Thanks for answering all the questions. I would encourage if there is a follow-up question I see on the Slack. So please go over the questions that we couldn't answer, as well as people, if they want to post more questions, then please go there and answer them offline. Thank you.
Thank you.
Okay, now let's have our third speaker. So Yiqi Zhang. So Yiqi Zhang graduated with a master degree in software engineer from Xi'an Jiaotong University in 2018. And Yiqi has worked in Samsung Research and Development Institute, China, Xi'an, for 3 years, and mainly engaged in storage optimization, including data placement and SSD reliability research, and so on. So let's play the video.
Hello everyone, I'm Yuxi Zhang from Samsung Research and Development Institute, China, Xi'an. I'm very pleased to join this workshop. The topic of my paper is automatic iOS management based on file characteristics. My presentation will include these 5 parts. First, some background and our motivation of this research. Second, our analysis of common files in various workloads. Third, I will introduce our scheme, file stream, and then the experimental results will be shown. Finally, the conclusion and our future work. There are some issues in performance, cost, and reliability of SSD, such as reduced performance and short lifespan. GC has a major impact on both performance and cost. As we all know, GC copies validated from the victim block to another block. It consumes bandwidth and may affect user I/O. The copied data also leads to write amplification. This shows the lifespan of NAND flash. If we place data according to data lifetimes, data within the same block can be invalid at nearly the same time, and the copied data will be reduced. This is our overall idea. Analyze various workloads, recognize data patterns, analyze and estimate data lifetimes, and finally group data. Dynamic data placement policies are generated to improve performance and lifespan and reduce our latency. In this paper, part of this work has been done by machine learning, and we hope that AI can do most of the work in the future. In addition, this paper is based on multi-stream technology. Data carrying different stream IDs are placed in different blocks of SSD. There are lots of data, lots of I/O, so the stream assignment schemes are based on data units. AutoStream and LKStream are based on the characteristics of LPA chunks. PCStream uses program contexts, but there are also data lifetime differences in the above data units. And to obtain these characteristics, application code or kernel code need to be modified. This makes the deployment on product environments difficult. File is a natural data unit. It has 3 advantages. First, the access patterns of data within the same file are similar. Second, there are many file characteristics. Third, Linux provides some tools to obtain file characteristics, such as iNotify. For data files in various databases, we found 2 main types of files: append-only file and in-place update file. Append-only files appear more in key-value LSP-based stores, such as USB and Cassandra. These files are log-structured files. Data are usually not updated inside the file and are invalid only after the file is deleted. As data are updated, files are frequently created and deleted. In-place update files appear more on Circle database, such as MySQL and PostgreSQL. Data are updated inside the file and are invalid when they are covered. These files usually exist for a long time, and they are created or deleted when the tables are created or deleted. Let me first analyze the append-only file. The finger shows an example of create, write, delete of OTB files. We can get 3 observations. First, these files are frequently created and deleted. They finish writing very quickly, and a few files write at the same time. Second, the data lifetimes within the file are similar and can be reflected by the file lifetime. At last, the same type of files may have similar lifetimes, such as write-ahead logs, while different types of append-only files usually have different lifetimes. Next, in-place update file. The finger shows an example of table file writes in MySQL and PostgreSQL. We can see that the update frequencies of data in different files are quite different, and the update frequency in the same file is relatively similar. The update frequency is related to the data lifetimes, since data are invalid when they are overwritten. We propose the unit size modification, the ratio of the number of modifications to the file size, to reflect update frequencies. The architecture of our file stream is shown in the finger. File monitor captures the file characteristics and stores them in the file attribute table. Stream Manager maps or remaps each file into a stream based on these characteristics. Stream Manager has three modules. Mapper assigns stream IDs to files when they are opened. Remapper reassigns stream IDs to non-opened files. And Divider allocates different stream IDs for the mapper and remapper. Next, we will introduce these three modules in detail. First is about mapper. Some files complete writing very quickly, as in many open-only files, so it's necessary to assign stream ID to a file when it's opened. That's what mapper does. Since the data lifetimes within the file are relatively similar, our first idea is to minimize the mixing of data between different files. We estimate the amount of data to be written in existing files. Smaller amount of FI means less data will be written to FI, and thus less data will be mixed with the new file. Our second idea is to minimize the lifetime difference between files written to the same stream, since most of the newly opened files are open-only files, and their lifetime can represent the lifetime of their data. In order to estimate the lifetime difference between FI and FO, this equation calculates the average lifetime difference between the files of the same type with FI and FO. We consider files with the same parent path and extension as the same type of files. Smaller DIF, FI, FO means the lifetimes of FI and FO are more similar. Then we want to combine the above two factors, so we multiply them, and we integrate the scores of the existing files of stream S as the final score of the stream S. Suppose the new file is mapped to the stream S. A smaller score indicates that less data of different lifetimes will be combined within the stream. Therefore, mapper selects the stream ID with the lowest score and assigns it to the new file. Next, remapper. Some files remain open for a long time, as in many in-place update files. They may face the changes of workload stress. Remapper is responsible for reassigning stream IDs to non-opened files regularly. As I mentioned before, the data lifetimes of these files are usually related to the update frequency of data, and we propose USM. We cluster files based on their USM by keys every t seconds. As the update frequency changes, the file will be remapped to a corresponding stream. Then we think that when the workload is stable, the clustering operation is not necessary. So before each clustering, we calculate the distances between files and the previous cluster centers. If files are still closest to the previous cluster centers, we think the workload is stable, and thus skip the clustering operation. This actually reduces the resource consumption and the fluctuation of the remapped stream IDs. Divider is responsible for dynamically allocating different stream IDs for mapper and remapper. That's to say, adjusting D. We consider who manages more files, or whose files more data are written to, who should occupy more streams. We calculate the proportion of the streams that mapper should occupy by the number of files managed by mapper and remapper, and the total number of their modifications. Then we adjust D and run D regularly. Next, we show our experimental results. We evaluated the file stream on real Samsung multi-stream SSD. It supports 8 streams. The experiments are performed on 6 workloads, as shown in the table. We compare file stream with a baseline without displacement and 3 existing displacement schemes. AutoStream and LKStream are automatic schemes. They assign the stream IDs to IO based on the exact characteristics of LBA. ManuStream is a manual scheme. Programs analyzes the application mechanism and fix stream assignment strategy into application code. In addition, the key parameter T is set to 1 minute by default, and is discussed later. This figure shows the rough values of the file streams on the 6 workloads. We can see that file stream significantly reduces rough compared with other schemes. File stream performs well on all 6 workloads. This figure shows that file stream improves throughput compared to other schemes on most workloads, and it performed very well on ZooCD and Cassandra. Then, we verify the effectiveness of each module in file stream on 3 workloads. ZooDB has many frequently created append-only files, so Mapper performed better on it. MySQL has many long-term in-place update files, so the Mapper performed better on it. The combination of these 3 modules makes file stream optimal. T is a key parameter in file stream, so we discuss it. In general, we can see that file stream is not highly sensitive to this parameter. This table shows the CPU usage of baseline and file stream. The increase in average CPU usage and PP usage is negligible, so file stream doesn't consume much resource. Finally, our achievements are summarized as follows. First, we propose a file-based automatic stream management scheme. It greatly reduces WAF and improves the performance of SSD. Second, we propose to estimate the mixing degree of data with different lifetimes to separate the data of newly opened files. Third, we design a new feature to reflect the access patterns of long-opened files, and we use machine learning to group files. In the future, we will apply our scheme to more devices such as zoned namespace SSD. It streams to hundreds of zones. We may also combine file information and LBA-related information. That's all. Thank you.
Okay. So Ichi, can you turn on your video? Okay. Yes, thanks for your talk. So there are some questions here. So the questions from Jenke from FIU is that what are the advantages and the disadvantages of file level information and versus the LBA level information?
Okay, file level information is higher level information. It's easier to perceive the workload pattern of host application. The access pattern of each file is usually consistent and easy to identify. This is also conducive to the analysis and estimation of the data lifetime in the file. However, file level information is difficult to perceive the fine-grained data in the file. In contrast, LBA level information can better perform fine-grained analysis of data. But because it's low-level information, it's difficult to perceive the workload pattern and data pattern. It may be better to combine the two information for analyzing the data lifetime.
Okay. So another question, Brian from Santa Cruz University, is that the file stream works under the VFS layer, but the underlying file system is also responsible for changing the lifetime of the data. So for example, the in-place update file system versus the log structure file system. So how does the file stream address this?
Now our scheme is mainly suitable for in-place update file system such as EST4 and XFS. For log structured file system, file stream may also work, but we don't try.
But I think the question is that how the underlying file system implementation is going to change your solution.
Log structured file system such as F2FS will change the lifetime of data, but if the data is invalid on the VFS, the data is also invalid on the file system. Sometimes the data lifetime are changed. And now I can't estimate the degree of the change.
I see. I have a follow-up question is that, does your system have dependency on the file system implementation? If that's the case, do you think it's a better idea to offload the detection to the device level, like the first question, the LBA level?
Yeah.
Mm-hmm. Okay, so another, I have one more question is that, among all the information you collected, so what's the most critical one for the GC performance according to your study, right? You collect a lot of file information, but what's the most critical one?
I think for in-place update files, modifications is the most important attribute because it reflects the data lifetime of in-place update files. For append-only files, the lifespan of the file is the most important because the data and the file are invalid together.
Okay. One more question is that beyond the heuristic-based approach, can you comment on the potential of using machine learning algorithm for prediction? For example, when you open the file and you based on some analysis, you can predict the file lifetime in advance. Did you try that? Or did you see any potential of doing this?
I think the prediction is possible, but it is very difficult to collect the online information on product environment. The test environment can't show the effectiveness of prediction.
Okay, thank you very much. Thank you for your talk and great answers. Okay, so now let's move to the next speaker. So our next speaker is Umesh, and Umesh was a founder and the CTO of Nimble Storage, and which combines the best of flash and the disk drives. And for the last year, and Umesh has been enjoying his time as an independent researcher. So let's play the video.
My name is Umesh Maheshwari, and I'm here to suggest that we move beyond block storage to add device-level support for variable-size pieces of data, which I call ROCs. Now, we all know about the block storage abstraction. It presents a sequence of fixed-size blocks that can be read and written randomly. Some of you might also know that the SSD industry is moving to standardize a new abstraction called zoned namespaces, which divides the block address space into large zones and requires that each zone be written sequentially. This abstraction still uses fixed size blocks. So to avoid confusion, we could qualify the original abstraction as conventional block storage and the new abstraction as zoned block storage. Given this context, I believe that sequential writing presents a great opportunity to store variable-sized pieces of data, or ROCs, and that we should leverage this opportunity by extending zone storage to support ROCs. Most of my talk is about why it makes sense to take this second step to extend zone storage this way. But first, let me expand on why it is useful to take the first step, which is to introduce zone storage, especially for flash-based devices. Suppose we want to implement a key value service. We could use a B tree or an LSM tree to translate keys to block addresses. Either way, it requires a largish map and causes write amplification. And after the host has done this heavy translation, the SSD must do another heavy translation from block addresses to flash locations, which again requires a largish map and garbage collection. This is where zoned storage could help, but it depends on whether we use a B tree or an LSM tree. In either case, the SSD can map a zoned block address to a flash location with only a light translation, without a large map or GC. With a B tree, the heavy translation from the device must be pulled into the host in the form of a log-structured file system or device mapper. But with an LSM tree, the key can be mapped directly to a zoned block address, thus eliminating one of the two heavy translations for good. So, assuming we want zoned storage, I believe we should extend it to support rocks because the downside is small and the upside is significant. I'll first talk about why the downside is small. One might think that rocks might complicate the specs, but really the specs for zoned rock namespaces, or ZRNS, could be very similar to that for ZBNS, as I've shown here, only the addressing is slightly different. In ZBNS, a zone is identified using its starting LBA, and the block address is the sum of the zone start LBA and the block number within the zone. In ZRNS, a zone can be identified using its starting offset in bytes, and the rock address is the sum of the zone start offset and the rock offset within the zone. Another option is to create the rock address as a tuple of the zone number and the rock offset, which has somewhat cleaner semantics. One might think that rocks would add a lot of overhead in the SSD, but as far as I can see, the overhead would be small. First, let's consider how an SSD might implement a zoned block namespace. It can map a zone to one or more flash erase units, and this requires only a small per zone map, not a large per block map. The only challenge is that a block is typically 4 kilobytes, while the unit of programming NAND flash is a page, which is typically 16 kilobytes. So a single block cannot be written directly to flash. Most SSDs address this challenge by staging writes in internal NVRAM, and for this the SSD needs only a page size buffer for each active zone, which is a relatively small amount of NVRAM because zones are large and only some of them are active at a time. The same setup can work for staging rocks because NVRAM is byte addressable. Also, as with blocks, there's no need for a per rock map. In fact, the only per rock overhead is the metadata embedded inside each rock, which could be as small as a 2-byte length and a 2-byte CRC. This means the SSD could support rocks as small as, say, 16 bytes. And note that the host can always read or write a large sequence of rocks with a single command. So far, I've talked about how rocks would not add much cost in terms of either complexity or overhead. Next, I'll talk about how database and file systems can use rocks to store data more efficiently. There's a longer list in the paper. Here, I'll touch on only 2 of them. Some data, such as database pages, are quite compressible. So it's useful for the underlying file system to compress such data transparently. The challenge is that compression turns fixed size pages into variable size pages. Let's discuss 2 techniques used in current file systems on top of block storage. The first technique is to compress a cluster of pages and to store it in an integral number of blocks. The good news here is that the file system can continue to manage storage in units of blocks. For example, the unit of garbage is a block. The bad news is that if the application updates a page, the file system has to read, modify, write the whole cluster. So this is not good for random writes. The second technique can be seen as implementing a ROCs-like abstraction on top of block storage. The file system does need to be a bit more sophisticated. For example, it now needs to collect garbage in units of ROCs. But now, if the application updates a page, the file system can rewrite just that page. So these software level ROCs or soft ROCs can store data efficiently, but they are still not as good as device level ROCs. Here I've shown device level ROCs to the left. For soft ROCs, the file system has to read an integral number of blocks. For example, to read page 1, it has to read block 0 and block 1. With device level ROCs, it can read just the desired ROC. This would not matter much for spinning disks, but it can matter for SSDs by saving memory and I/O bandwidth. Device level ROCs have some other advantages, which are covered in the paper. Let's move on to the second use case, which is logging. Zone storage might seem like a natural fit for logging, but one problem is that log records can be much smaller than a block, possibly by a factor of 100, and each record might still need to be persisted as it arrives. With block storage, the host can use one of these two techniques. The first is that it can rewrite the last block in the log, possibly 100 times. Actually, zoned storage doesn't allow any overwrites, and this requires an extension called ZRWA. Even with ZRWA, there can be at most one write pending to any given block, because otherwise the device might reorder the writes and lose some records. The second technique is to stage the writes in the NVRAM. Note that this staging is explicitly directed by the host and is on top of any implicit staging within the SSD. So it adds some cost and complexity to the host. With device level ROCs, which I have shown here to the left, the host can append log records directly to the SSD without staging them in NVRAM. In fact, multiple threads can append records concurrently without synchronization, and this can be particularly useful if the device is attached to the network and the threads are on different hosts. All of what I have presented is conceptual, and it would be useful to implement and evaluate these concepts and to build on them further. For example, it would be useful to evaluate ROC-based logging in the context of a real database system. Second, one could implement a device mapper that provides transparent compression to conventional applications. Third, one could extend ZRNS further to offload I/O from LSM trees. If each KV record is stored as a ROC and the device understands the KV format, the device can perform zone compaction while the host retains control over the merge policy, and this would support a variety of LSM designs. To conclude, I believe that zoned storage has the potential to become the dominant abstraction on flash-based devices. I have uncovered an opportunity to extend zoned storage to support variable size ROCs, and I have theorized that this extension would add little cost in terms of either complexity in the specification or overhead in the implementation. I have argued that file and database systems can leverage device-level ROCs to store data more efficiently and also to append log records concurrently. Finally, I think we can extend zoned ROC storage further to optimize domain-specific functions, such as merging in LSM trees. Thank you, and I can take questions now.
Okay, thank you. Umesh, can you turn on the radio? Hello? Umesh, are you here?
Yeah, sorry about that.
Okay, yeah, great talk. So let's start the questions, right? So Janky from FIU asked questions that what are the implications of the ZRNS on the housing keeping overhead of SSDs such as GC?
Right. So with ZNS in general, GC is performed at the host, not on the device. And with block-based ZNS, which is what we have today, the unit of garbage collection is a block. With rock-based ZNS, it will have to be a rock. Okay. So it's slightly more complicated than block-based garbage collection, but it can be done. And I know of 2 systems that actually do it. So it's definitely practical.
Okay. So audience, please keep posting questions here. And at the same time, I have some questions. So will the rock storage require applications to decide the size? Because you actually provide the flexibility to use different sizes, right? The interface, but does it require applications to specify the size?
So different rocks can have different sizes, obviously, within the same zone namespace. And then it depends on the application. So if we are thinking about something like transparent compression, which I talked about earlier, then that's completely transparent to the application. In fact, the file system inode structure might also not need to change. And only the lower layers, which stores each block as a compressed variable size rock, that will need to change, and that will specify the size of the rock. But if we are talking about other applications, such as write-ahead logging, then I do think it should be exposed to the application and we might not want to use a POSIX file system interface for that. We might want something which explicitly supports appends, and perhaps appends with a discrete log, not just a continuous stream of bytes. Mm-hmm. So that's that. Yeah, so it depends on the applications. For LSM trees, for example, if each KV record is stored as a rock, then obviously it will be a variable size, and it will depend on the application will specify the size of the KV record. Did that answer the question?
Yeah, and there's another question from Brian from Santa University. And can you share your thoughts on how ECC should work on variable size data? So ECC is typically encoded on same fixed size. I think that's a good question. Yeah.
Yeah. No, that is indeed a great question. So, yeah, ECC is generally done in hardware, and I think it will, continue to be done with fixed size code words. Like today, it's about 2 kilobytes. And a 4 kilobyte logical block might include 2 ECC code words. So I think within the SSD controller, the SSD controller would still need to access data read data in units of ECC code words, so it can perform the ECC. But once it has done the ECC, then it can pick the parts that are of interest and convey that to the host.
Okay. So another question from Abitali from Penn State is that, is there any data on how much benefit performance versus storage saving rocks provide over blocks? And why can't we just use the padding to pad rocks to complete the blocks?
Okay, so for the first one, I don't have any data. This is a conceptual proposal. But I have talked about logically, what's the benefit with respect to either not requiring padding, or alternatively, when padding is not used and we store logically different pieces of data in the same block, then we often have other issues like read modify write in some cases, or some sort of an amplification in the number of bytes transferred, things like that. Okay, so so padding rocks would, depends on how big the rocks are. If you're talking sizes of records in a write ahead log, those log records could be very small, could be less than 100 bytes, right? So to use a 4 kilobyte block for such a small record would be very wasteful.
Yeah. So we have some time, so we can discuss more questions. So there's one question from Raju, and so his memory is perhaps outdated, but don't flash chips need to be programmed and the page granularity like 1 KB? Any comments on that?
Yeah. In fact, the page granularity is more like 16 kilobytes these days. It keeps on going up with the flash density. And I touched upon this in the presentation too. So in fact, what that means is that there is already a challenge with fixed size blocks, even with 4 kilobyte blocks. You cannot write a 4 kilobyte block as it arrives to the SSD directly to flash, because flash needs 16 kilobytes, right? So for that reason, the SSDs do some staging or buffering within NVRAM inside the SSD. And my point is that the same staging and buffering can be used to buffer variable sized rocks, because NVRAM is byte addressable. And that's what makes the whole thing, the ability to write rocks practical, I think.
Yeah, there's a follow-up question from Jenke. So can you please provide the pointers to the mechanisms you mentioned that handle GC and the granularity of variable size rocks?
So the file systems that do garbage collection at the rock level include Sizzle from Data Domain. And these are just the ones that I know about. And they include Castle from Nimble Storage. I think there's a paper on Sizzle from Data Domain. I don't know if it goes into garbage collection or not.
Yeah, I have one more question. Okay, so follow the keynote speaker, right? He mentioned that the open channel, the complexity of using the open channel SSD. So, but do you think the rock interface could bridge the gaps between the zone SSD and the open channel SSD? So actually, you wanted to offer more flexibility based on the zone SSD.
No, I wouldn't say that it's doing anything with respect to the gap between the open channel and the zoned SSDs. Zoned SSDs are basically raising the level of abstraction a little bit further above where open channel SSDs were. Basically, they add a level of mapping at a coarse granularity, at the zoned level, right? And that mapping is useful to have, as the keynote speaker said, because without it, you have to worry about exactly, the physical location where the data is going. With that little layer of abstraction, a zone can be remapped for wear leveling, for example. Okay, at that coarse level. So it provides a useful level of abstraction or isolation that is desirable, as the keynote speaker also said. So that particular aspect is not being changed with this, extension from fixed size blocks to variable sized blocks.
I see. Yeah. Okay. Thank you very much, and thanks for the great discussions here. I think that's the end of this session, and thanks everyone for attending this session. And we are going to have a short break.
Okay. Thank you.
Yeah.
Thank you, everyone. We'll get back for the next session at 12:55 Eastern Time. See you all there. Bye-bye.
Yeah. Bye-bye.
Okay, so welcome to session 2. Sudarshan, are you here?
Yep, I'm here.
Okay.
Should we wait for another couple of minutes before we start? Sure.
We'll start in maybe 2 or 3 minutes, yes. Just a kind of reminder for our audience, so please post your questions on the Slack channel. So we have one thread for each paper. This is session 2, distributed storage systems. Okay, so we have people from around the world with different time zones. So probably somebody is in their midnight for those people in China, I know. I think we can go ahead and start. So you want to go ahead and start? We cannot hear you.
Just give me 1 minute. I think one of the presenter for the third paper would not be able to join. And instead of the presenter, it will be Alexi who would be presenting. The co-author would be handling the questions. All right. So let's get started. Welcome all to the second session on distributed storage. We have 4 exciting papers on different range of topics, from near data processing to handling large-scale distributed storage, concurrency issues, and so on. Ben and myself will be chairing the session. So please post your questions on the Slack channel. There is a thread for each of the paper. We'll keep monitoring the Slack. All right. The first paper of this session would be about enabling near data storage processing for distributed object storage systems. And Ian from Intel Labs would be presenting. So Ian is a storage systems researcher at Intel Advanced Storage System Lab, and his focus is on computational storage and distributed systems in general. Please play the video.
Hi, folks. Thanks for watching the talk today. My name is Ian Adams, and I am going to be talking to you about our work on enabling near data processing and distributed object storage systems. Specifically, this is work about doing some pre-processing and data layout to make sure that things are well laid out within a software-defined storage system so that you can actually have easier near data processing and computational storage capabilities. So what do I actually mean here? Well, NDP has kind of a data distribution problem. Now, NDP, or near data processing, it's actually a pretty simple concept. Move the compute to the data to reduce your I/O traffic. But modern distributed storage systems make this tricky. In particular, sharding and striping systems don't respect semantic boundaries. So what do I actually mean here? So let's say we have 4 servers here, and we lay out 2 data stripes and consider each one of these numbered boxes to be some sort of data element, like a picture or a record or whatever. And as you can see, these things highlighted in the red boxes, 4, 6, 11, they're crossing shard and sometimes stripe boundaries. And when you're trying to do near data processing, suddenly you have a coordination and collation problem. So how do current systems actually deal with this? Well, some systems just punt on the issue, like they assume you've got replicas on each individual node, or they do data collation, like MinIO has a version of what they S3 select, which is a data filtering function. And if you look at the data movement internally, what it does is, even though it shards the data natively, it internally centralizes it, so you get a lot of data movement, even if you're really only interested in filtering out just to get a few replicas. And so this erodes near data processing goodness, and it can make life hard also for computational storage devices, which may not have any awareness of this higher level structure. Others go for application-specific approaches. Now, things like Ceph Skyhook has application awareness for data placement of tables. Some MapReduce applications have record boundary awareness for internode reads for things like CSV records and so forth. Now, these are perfectly valid solutions, but they can be difficult to realize in practice. And in particular, they can be difficult to retrofit or extend into general purpose systems. So what we're looking at is, we just kind of was like, well, can we just avoid this problem entirely? Can we just not do that? And well, more concretely, what we're asking is, can we lay data out in such a way that we can avoid these boundary conditions? Can we just make sure that individual data amounts don't cross between servers or devices? Second is, can we do so without having a lot of application-specific baggage to the underlying storage system? Now, in some cases, this is going to be unavoidable, and it may even be desirable, but we do feel that this kind of raises the bar in terms of making it a little more difficult to have general-purpose near data processing. And we also want to do, can we do so in such a way that we have simple near data processing without a lot of this storage system awareness? And we think that the answer is yes, we can. We can do this data alignment from actually the writer's side, just with a few hints. And we're going to talk more about that next. Before we dive into exactly how we accomplish this, I want to give a little bit more sort of a background and observations on what motivated us to take this approach. So the first one is that lots of useful operations can be done on what we think of as data elements. These are things like keyframes in a video, or row groups of columnar data, or individual lines in a CSV file. The second is that distributed storage shards data at relatively coarse granularity. Now, in contrast to traditional RAID, which may distribute data in very small elements, 4 kilobytes, 64 kilobytes, things like that, these larger systems can erasure code things in large chunks like that, may be many megabytes inside. And given that we have this concept of a data element, we can fit many data elements within any individual given shard. And finally, storage systems, even those that rely on pseudo-random placement, are still ultimately predictable. Shard and stripe boundaries are also themselves predictable. So for example here, if we had a string 1, 2, 3, 4, 5, 6 distributed across 3 shards, we may be able to predict that, okay, each one of them is going to get 2 characters. So with this in mind, I want to give a quick bit of intuition behind how we actually align data. So this looks like the example we saw earlier. We have data elements, 1 through 6 here, and some shard boundaries, and we can see 5 and 6 are misaligned. They cross those boundaries, which will make life a little bit hard. Our idea is actually quite simple. just insert some padding to kind of nudge those data elements a little bit in the direction, so that we can ensure that each individual element is completely resident on a single server or device or node, whatever your unit of division is. So now let's dive a little bit deeper into what this looks like in a striped environment for a distributed storage system. In this case, this is a lot like what MinIO uses, but other systems will often look similar. So stripes are written across shards and are predictable in their sizes. There's often an upper limit or a fixed configuration. There may be some dynamic sizing as well, but we'll talk a little bit more about that in the paper. We're only going to touch on that briefly here. And what we call a stripe unit is the element of a stripe that resides on a single shard. And basically, the notion that we have is that we can use stripe unit sizes to generate those alignment hints. And those alignment hints are just byte offsets that delimit where a stripe unit border is. And with these hints, we can tell when a data element will be in a boundary condition when we're doing pre-processing or as we're writing data out to the software-defined storage system. So how do we actually generate these alignment hints? Well, when it comes down to it, it's just integer arithmetic. Now, keep in mind, this is a very quick overview. There's some edge cases and things. I suggest you take a look at the paper for more details on that. But really, there's three things we input into a stripe unit hint generator. That's the maximum size of a stripe, how many data shards that stripe is being distributed over, and the size of a particular batch. So let's say in this example, we have a maximum stripe size of 10 megabytes and 4 data shards we're working with. And if our batch size is above the maximum size that we can write in a stripe, it's a pretty straightforward bit of integer arithmetic, 10 divided by 4. Our stripe unit hints are 2.5 megabytes per stripe unit. If we have less than that, and we have something like a dynamic stripe size to deal with, what we do is we actually overestimate our size a little bit, just so we have some wiggle room to use that padding so that we don't overshoot. And once we have these hints, the data elements are just laid out within the bounds of those hints, and the unused space is padded out. So here's a quick example of what this might look like in practice. So first is, let's generate these stripe alignment hints. We're going to input the batch size to the hint generator and the layout parameters. At that point, we have a set of alignment hints to work with, and we can start laying out our data. We fill the area with data elements and padding. So imagine these boxes are data elements, and okay, we get to the end, that's padded because we know the next one is going to be too big to fit within the remaining space. We can just do a greedy algorithm here. And at some point, we filled out the stripe, and then we track that padding and save those offsets as metadata for later use for either stripping them out or using within the near data processing system. And then we can write that stripe to the storage system itself. It's a pretty straightforward process. We're going to wrap up here by quickly talking about our proof of concept, which is doing CSV data filtering using our aligned data method in MinIO, and we actually process that data via containers we can deploy next to the stored data shards because everything's aligned. So very quick overview of our experimental setup here is we had a 4-node, 2+2, 2 data, 2 parity MinIO deployment. We used the publicly available CityBike data set, which is a CSV data set. We used alignment hints to pad and align the data to fit within the stripe layout of MinIO. We had a simple filter query that selected around 25,000 records. And the container service that we deployed offers SQLite functionality, and we compare this to the built-in S3 select. But for that one, we use unaligned data. And queries are issued from a separate node from MinIO. So what does this actually look like architecturally? Well, on the writer side, we input our raw CSV data into an alignment app that makes use of our hint generator, and it outputs that aligned CSV data, which we then put to MinIO. And as you can see, there's 2 data, 2 parity. And because of this, we can reduce the need for coordination and enable simple parallelism. And so we can actually deploy those filter services as containers right next to those shards. S3 select, which we don't show on this diagram, that requires collocation at a MinIO node, which will become apparent next. So quick overview of the results. Well, the short view is it works, and we can trivially parallelize many filtering operations. And compared to the built-in filtering, we significantly reduce data movement. Now, what I want to quickly call your attention to here is these dark blue bars. That's data movement from S3 select, because it's having to write data out to a central point that then does all the filtering there. So 3 and 4 are actually pushing their data to 2, where the filtering occurs with S3 select. While with the blue bars, with our co-located containers, we're just returning the results to the client directly. So this will vary some on selectivity, obviously, and some correlation may still be needed for different queries, for example, a sum. I also want to point out that we had very low overhead in terms of both the padding and the metadata, and total was less than 8 kilobytes of additional data storage needed. So there's lots more to do here. So what we started with was a very simple example. This is a good start, but as people have rightfully pointed out, what about more sophisticated data types? We mentioned things like video. We also want to look at columnar data, maybe batches of images. We also think that storage systems should provide more native support for NDP. And this is actually a fairly low bar in our opinion, where it can be as simple as things like providing some information about how data is laid out in the system. Tell us where you placed a particular shard. And finally, there's things like quality of service, because now we have a fairly complex distributed scheduling problem where you also have, foreground traffic. People are going to be doing regular puts and gets, as well as potentially taking CPU and accelerators to do these operations as near data processing functions. And with that, I want to thank you for your time, and thanks for watching. And please reach out with any questions or comments that you might have. All right, can folks hear me okay on the line?
Yes, yes, we can hear you. Can you please enable my video? For some reason, I think it's not able to enable it. Yes.
Yeah.
All right. Thank you for the great talk. I mean, seems like a very pragmatic and an interesting approach to solve this misalignment problem. I'll look through some of the questions in the Slack channel. Maybe I'll start with the question I had this seems like a very neat idea, but the question is like, how much space amplification would it add beyond like the CSV? For example, let's say if you're going to pack for a video server. The second question is, would the padding increase space amplification over as time increases and the longevity of the data increases?
Excuse me. I think the overhead of the padding is going to vary wildly depending on the type of data you're using and the size of the shards you have to work with. Like, for example, I was recently looking at splitting video data into constituent pieces so we could fit them within these stripes. And if you have a fairly large chunk that you have to deal with in video, you have awkwardly sized stripe units, your overhead actually might be quite high. It might be upwards of 50-60% because you can only fit a single video chunk in each one of those shards, and the rest you have to pad out. But things that are at a finer granularity, you might have much lower overhead. And so there's some knobs we need to play with here. And will the padding increase over time? I'm not sure I quite understand the question. I think the answer is no there, but I'm not sure I understand what's being asked.
So the question is like, if you keep padding for like every 10 minutes, you're just keeping on adding more and more data with padded content. Is it going to increase the space more and more? So say, for example, is it going to be like 10% of the entire data storage or 15%? So what's the estimation, do you think?
Got it. I see what you're saying. So if you keep adding more and more objects that are themselves padded, it's just like, yeah, you're going to keep eating away at space there. And this is sort of as more further reaching as this is pontificating a little bit. We've looked at sort of, in my research, we've looked at sort of two extremes. We've had, let's make the storage system be able to handle all these data, detailed semantics. And now we're saying, let's just tell the writer what the storage system is doing and make them deal with it. And I actually think that we need to have a middle ground here where both sides can collaborate. Like maybe a writer can say, here's where my dividing points are. Can you adjust the stripe sizes in such a way that you minimize your overhead? Because I feel like, honestly, after I finish this paper, I feel like either extreme is inappropriate. There needs to be some place in the middle, but I feel this is at least a step in the direction of, okay, we can do this sort of cost benefit analysis of, okay, if I want to spend a little time spending some overhead and costs on that, I can make my life much easier for doing things like near data processing, because I don't have to worry about the complexity or as much complexity in moving data around when I have these boundary conditions.
So a related question is from Somali Chatterjee. Do you have like some idea about in terms of like the trade-off with respect to performance that you can get from padding versus the space? I think you've already answered the space part of it. So yeah, the performance aspect.
The classic agonizing engineer answer of it depends. You've got for some of these things, if you have very simple filtering operations, I think the performance is absolutely worth it in terms of you are simplifying the implementation of these near data processing functions, as well as reducing the need for internode collation and movement of data. But for some of these things, like if they are we've looked at, like if you're trying to do something that's, for example, is extremely CPU bound, it might be that the cost of moving that data is just, it's so cheap, just go move the data. This is one of the things I want to make absolutely clear, that while we're trying to chip away at this problem, we're under no illusion that this is going to be some solution that's going to solve everyone's issue. We're saying is like, here's another tool we can use to make a decision on whether or not we should move the data to ourselves, or we should try to push it closer to the computations closer to the location.
All right, great. The next question is from Ben He from Temple University. Is the hint generation done at the metadata server, and do you foresee that this hints has to be frequently updated?
Going to depend on the nature of the object storage system. Like for example, like with like things like MinIO and Swift, you actually have a remarkably small number of parameters. So if these either out of band, you can be given from an administrator, or you can just query a server that says, tell me your stripe size, tell me, a few other pieces of data that can be entirely generated on the client side. In fact, when we did our implementation, that's what we did. We knew that our MinIO deployment was of a particular type. We knew that it had a maximum stripe size of 10 megabytes. And from that, we could calculate everything on the client side with no other interaction from the server. In a more dynamic environment, and that's one of the things I kind of alluded to, is I think it would be nice if future designed systems were a little more sort of collaborative and a little more open, or if they even expose simple APIs to be like, could you tell me what you're doing so I can generate these hints myself and stop bothering you?
Great. So we'll have time for one quick question, and this is from Janki Bhimani from Florida International University. From your experience, what implications would you have on the tail latency, and are there any precautions that you would like to suggest to minimize the overhead?
That's a really good question. I think this gets to the general thing. Is the short answer is it will absolutely have an impact. And that's the second part of that answer is I don't have a good feeling for what exactly that is right now. I think that is a good research question. We are looking further at that. That's kind of what I talked about quality of service, where we wanted to be able to, we need to start thinking more about, we have a much more complex distributed computing problem now. And I would look at things like, there's some good work out there on like heterogeneous computing and heterogeneous scheduling that I think is going to be applicable to this area.
All right. Thank you so much for answering all the questions. And this seems to be a very pragmatic and interesting work. We hope to see it in a bigger venue soon.
All right. Thank you very much.
Thanks. All right. So the next talk would be on CRDTs on truly concurrent file system, where Romain will tell us how to build large-scale distributed systems for specifically geo-distributed file systems. Romain is an R&D engineer from France at Scality, and he's working on this project on building large-scale distributed file system, which is a part of a larger project called Rainbow FS research project. Can you please play the video?
Hello everyone, I'm Romain Vaillant, and I'm going to talk about CRDTs for truly concurrent file systems. In this paper, we present our work about building a highly available geo-distributed file system using only conflict-free replicated data types that don't need any form of synchronization. Today, FastM are probably the most used tool to share, edit and store information. While at first they were designed to work locally only, FastM that span multiple clusters across the world are widely common. Although they are very different to what we had, they still need to support legacy applications and command interface, such as POSIX. You can't expect applications to adapt to the specific behavior of your file system. These geo-distributed file systems also have a bit fair of requirement. They need to provide low response time across the globe, be always available, even under network partition, and be able to support an ever-growing amount of data. High availability and low response time can be solved by building a weakly consistent system. However, this comes at a cost. To name a few, at least for file systems, you can have name conflicts, two files or folders created with the same name, divergent rename, moving the same file to two different places, or cycles, renaming one folder into another, and some other that I won't go through here. But first, let's focus on a common issue, name conflicts. In this scenario, Alice and Bob are far apart and can't communicate outside of the file system. They both create a file under the same folder with the same name. Once the connectivity goes back, what should happen? A common way to solve this problem is to use synchronization. We won't accept the creation of the file unless we have exclusive access to the parent folder. Not only this creates a contention point, in our example here, but Alice and Bob wouldn't have been able to use the service, because when there is no connectivity, synchronization is not possible. Existing cloud services solve this by renaming files. Taking our previous example, this would be like having a final state with report ND1 and report ND2. Most of them do this consistently, with an exception of Google Drive, which might present different results to different users. Unfortunately, renaming file is not really intuitive, because you need to know how the system will behave to predict it, and you don't necessarily that your file will be named as you expect. And you can't even know when this will happen. Furthermore, if your application is using implicit file, let's say a recover file, renaming from the underlying system will likely block them at an expected time. What we would like in our system is a system where user can build a simple mental model of the behavior. There is no need to know how it works or having to predict it. Avoid after-the-fact corrections, no one like folder or file jumping around while browsing, and prevent legacy applications from breaking when updates are merged by the system. To allow users to use their application in a shared workspace seamlessly, we think that those 3 points are very important. In our CRDT file system, LMRFS, we have the old concept of views. The system always favors the user performing the request and will show what's the best for the requester. If we take back our example, here both Alice and Bob receive their own file named as report ND, and the conflicting file as if a new file arrived at a different time with a different name. At this point, it is important to note that while the views are not the same, the state of the file system is. Names shown to the user here are only part of the interface. CRDT are perfect for solving this kind of problem because it's type that can accept independent and concurrent updates without any form of coordination. You can have two nodes given the same set of unordered updates, and they will converge to the same state no matter what. This is the strongest form of eventual consistency. With this property, you can have optimistic replication also. So you accept the update locally and dispatch it asynchronously. This gives you a very good response time because you can just apply it locally and reply to the request immediately. Whatever happens elsewhere, you don't care because the state will converge. So let's take a simple CRDT, a set. CRDTs come in a multiple flavor, and for a set you can have, for example, add win semantic or remove win semantic. With add wins, concurrent adds and removes will only honor the add. On the left, the concurrent add and remove operation for the same elements leads to only the add being taken into account. On the right, however, it's the reverse. Only the remove is taken into account and the add is ignored. The most straightforward way would be to use this kind of set to represent our directories. Simply storing a set of tuples, with each tuple representing a named reference in the file system. But while we will have the set that converge correctly, this doesn't solve any problem, because as before, you will end up with two files with the same name under the same folder again. You will still have a mechanism, you will need a mechanism to detect this situation, and then to fix it, you will have to perform more operations until the state goes back to something that is correct. Our approach in AlmaFS is to augment our tuple with a unique ID, a view ID. There is a strong requirement of this ID to be unique. When a user performs a request, it is implicitly associated with a view ID. When the set converges, we can still recover the information on who created the reference without doing anything. And we can match this request view ID with what we have in our state. On the interface side, the system will detect that Bob tries to refer to his file either by only specifying the name, report ND, or by also specifying the specific view ID in this case, report ND, Bob. In that case, after merging updates, user can resolve conflict simply by doing anything they want using standard FS operations. Or simply, if they want, they can do nothing and continue to work as normal. If Bob was using his application, for example, merging conflicting updates won't affect the application because from Bob's point of view, none of its files change, and for the application it's the same. So now, let's focus a bit on another problem, divergent renames. In traditional file systems, renaming is exclusive. In a weakly consistent file system, however, it is possible to have two users wanting to rename the same file concurrently. This situation acts as if someone just created a reference. Two directories entries are now referring to the same file. In a local file system, this is perfectly fine, for file at least. However, creating a reference is problematic because you can't use reference counting. Imagine two nodes wanting to read and only then increment the counter to the next value. It's a classical REST scenario. To keep the counter valid, you need synchronization. But it's not the end of all, because fortunately for transaction you can use CRDTs have transaction also. You can update multiple CRDTs together inside a unique transaction. You can use our reference format and keep another set that we associate to our entities, but we will update alongside the rename, NKD or mknode operations. So here we can see that both what the set will look like after a rename. A divergent rename. The original reference have been removed correctly, both operations deleted the same tuple, and in both cases they deleted the same tuple with the same view ID that they saw in the state. But since each request have a different view ID because it's unique, and in the best case you also have a different name, the two new tuples will be different. So the final set will have both values being added, no matter what. In POSIX folder, you can't have multiple references. If it is a requirement, you can simply add another CRDT that stores only the last reference that was created. That way, the last value of this CRDT will be the true parent. There are other problems, some of which we go in more detail in the paper. To name one again, you have deletion of inodes, for example, which is a tricky topic, because you need to ensure that at a point in time, the inode won't be referenced by anyone. And content conflict also, you can have, when you have a content conflict, you either need to merge the content with a specialized CRDT or bubble it up and act as if there were a name conflict. To build this system, we based our work on Anti.db, an open source CRDT database which offers geo-replication and interactive transaction. AlmaFS, our file system, is also available on GitHub. It's written in the Rust language and exposes a Fuse interface. From this solution, it is important to remember that CRDTs ensure that the state will converge, but not that the state is correct for the application. In our example, just using a set CRDT wasn't enough. As a designer, you need to think on how operation interacts and use a proper CRDT to solve your problems. Ideally, you will be able to use a set of CRDTs and combine them for the application's need. And if it's necessary, only this time you can use synchronization at the cost of availability and performance. This is called the just right consistency. We think that CRDTs are a great fit for building geo-distributed file systems. There are still some problems to solve, like cycles or space reclamations. Cycles, we started implementing 3 CRDTs, and we also need experiments on the interface side to know if the results are intuitive or not in comparison to other systems, and on the performance characteristics, of course. We'd like to compare MFS with existing file systems, both strongly consistent one and with the similar cloud services. Our current issue is that the implementation still lacks optimization for traditional file systems. Thank you. If you have any questions, I will be here after to answer them.
Thank you, Romain, for the great talk, and this is very interesting. The CRDT approach seems to be like quite intriguing. As questions over in the Slack, I'll start with a question. I'm curious, like, what happens if, let's say, there is like 2 writers and one of they end up writing to the same block before one of them gets disconnected? How is the conflict for the same block resolved? Like, do you use something like a timestamp, or is there some other approach to resolving conflicts to the same block?
Hello. So currently, what we do is that we keep a timestamp and we overwrite the data. But that's not what I want in the future. Ideally, you will want to keep track of the records and the conflicting records, and then show in the file system the conflict as if they were a name conflict, so that people can see the different versions of the file and correct them as they want.
I see. Thank you. The next question is from Ben He. He asks, like, what are the, or how much of change is expected from application aspect or designers, specifically when there are conflicts?
So I would say that if you want an application that is solely based on CRDTs, you need to rethink everything, because every operation can conflict between themselves. And so you need to rethink about the state, how they will interact with the operations, and how they will converge. And you must have a great care on if the merging is the state after the convergence of the CRDT will be valid for your application. However, if you want, for example, have some parts of your application using CRDT, it's a bit easier. You can keep it isolated and only deal with that. So, for example, I think that Spotify use CRDTs for playlists. So it's always limited applications where it's easy to reason about. There are tools that are also developed to help with that.
I see. Thank you. I had one more question. Maybe I think this is something that it's ongoing. Like, do you have some notion of, like, in terms of like some initial thoughts on the performance that with compared to, like, say, for example, any of the previous studies that has been done in the space? Like, do you see that because this information has to be tracked, would this be impacting performance even for like regular operations, even when there is no conflicts? And what could ideally happen if there are conflicts?
So it completely depends on the CRDT that you used. For register, for example, for what we use for file content, the overhead is only a timestamp, basically. But the more you get complex CRDTs, the more the overhead in storage is important. So, for example, for a tree CRDT, you need to track a lot more of data. And so, yeah, currently, LMFS is not really performant because we focused on the convergence and the correctness of the file system. But I believe that if there is more effort on optimization, you can be on par with current distributed file system.
All right. thank you, and we hope that you could expand this paper to a future full publication. I'll hand over to Ben He for the next couple of papers. Thank you.
Thank you, Sudhir. Thank you. So just again, a quick reminder for our audience, please post the questions on the Slack channel where we have one thread for each paper. So our next speaker is Swarup Matt. He's going to present unifying the data center caching layer. Is it feasible or profitable? Swarup just graduated from Penn State this past May and joined Amazon as a software engineer. Now please play the video.
Hi all, today I'll be presenting our paper Scalable but Wasteful Current State of Replication in the Cloud. This work was done in collaboration with Alexei and Abu Talib. So strongly consistent replication, it's currently everywhere, and it's the backbone of modern cloud services ranging from cloud data stores to configuration management. And in order to ensure this strong consistency, all these services implement state machine replication primarily using consensus protocols. So henceforth, I'll be mentioning them as replication protocols. Okay, so one of the main objectives of these replication protocols is to achieve high throughput. Few examples of such cloud services and cloud data stores are Google Spanner, Yogabyte DB, Cockroach DB, Zookeeper, and many more. So how do these replication protocols try to achieve this high throughput? Let us consider a simple example of a replication protocol like multipaxos. As you can see in the image, in the case of multipaxos, the leader does most of the work by talking to the clients and also trying to replicate their requests. And at one point, it becomes a bottleneck of the system. So how do we optimize a replication protocol like this? One way to optimize this is to shift the load. Many protocols use this approach to shift the load from the bottleneck node to the underutilized nodes. A few examples of such protocols who try to shift this load are ePaxos, SDPaxos, and PigPaxos. And each of these protocols have a different way of shifting this load. So here we see how ePaxos is trying to shift the load and utilize more resources to achieve this high throughput. So let us now talk about the resource utilization of these replication protocols and how do they actually differ from each other. In order to do that, let us consider a simple example of taking three dedicated nodes with 2 cores each, and we will try to run an instance of multipaxos and ePaxos, and let's look at the resource utilization. So when we run an instance of multipaxos, we see that hypothetically, the leader occupies both the cores, but in the case of followers, they occupy only a single core, leaving one idle. Now, when we compare this to a complicated protocol like ePaxos, we see that it tries to shift the load and remove the bottleneck by shifting the load. And in doing so, it actually ends up utilizing all the cores and hence achieves high throughput, which is great for ePaxos. And this optimization helps in achieving very high throughput. That's great. So let us now look into this throughput increase and resource utilization. So we started with first confirming the performance gains of ePaxos protocol. So for that, we started with a simple experiment by running an instance of multipaxos and ePaxos with 50% write workload and targeting an in-memory key value store for about 60 seconds. And in this graph, we show the per second throughput over the course of our experiment. So as you can see from the graph, multipaxos achieves around 14K throughput, but ePaxos ends up achieving 18K throughput, which is about 20% higher, and it's in the similar ballpark as the ePaxos paper. So this is great for ePaxos achieving this very high throughput. But where does this performance gain actually come from? What's the missing piece which is not discussed? So this performance gain comes at a cost of resource efficiency, and this is nowhere discussed. So for the same experiment, we now look at the CPU utilization. And in this graph, we see that in the case of ePaxos, all the nodes hit a peak CPU utilization of 100%. Whereas when we compare this with multipaxos, we see that only the leader hits a peak utilization of 100%, and all the followers hit a peak CPU utilization of around 25%. So here we see that ePaxos with 500% utilization achieves 18K throughput, but Multipaxos with just 200% utilization achieves 14K throughput. So clearly Multipaxos shows better resource efficiency when we compare that to ePaxos. In order to better analyze the resource efficiency of these replication protocols, we introduce a new metric, which is throughput per unit of constraining resource utilization. We say constraining here because we see that resource is clearly the bottleneck of the system, and this constraining resource, whichever it might be, inhibits the scalability of the system. So in our case, in our experiments, we consider only the CPU utilization, but other factors like memory, network bandwidth can also be used as factors for analyzing this resource efficiency. So what does this metric do? This metric helps in determining the added cost of shifting the load and removing the bottleneck for these replication protocols. So let us now look at how this metric actually works for our previous experiment. So in this graph, we show the normalized throughput, which is throughput per unit of aggregate CPU utilization, which is our constraining resource in this case. And we see that Multipaxos has better normalized throughput when we compare it to ePaxos, which is great. Okay, Multipaxos has better resource efficiency, but why do we even care about resource efficiency? Why does it actually matter? So resource efficiency matters because all these replication protocols are actually deployed on cloud, which is pay-as-you-go utility model, and we need to be aware of the amount of resources we actually end up utilizing. And we have seen the replication protocols like ePaxos earlier, which try to optimize by shifting the load from the bottleneck node to the idle resources. But these optimizations are done keeping in mind that the machines are actually dedicated. In reality, all the databases are actually deployed on cloud, where resources are generally packed, leaving very limited to non-idle resources for these replication protocols to be utilized. Okay, so a few examples of such cloud databases like Google Spanner, Yugabyte DB, Cockroach DB, and many more are generally sharded, and they deploy a replication instance for each shard. And many such replication instances are generally packed together in cloud on the same physical machine. Okay, to explain this better, let us consider a simple example of packing. So in this case, we consider 5 nodes with 6 cores each, and we will try to pack multiple instances of these replication protocols. So in our case, we'll specifically try to pack multiple instances of Multipaxos protocol. Okay. So here we try to pack instance 1, and we see that the leader occupies 2 cores and followers occupy 1 core each, similar to what we have seen earlier. So, and moving on, when we try to pack instance 2, we see that the leader here is in machine 2, and the reason for this is due to many reasons like fault tolerance, high availability, load balancing, etc. And we see in the same format that the leader occupies 2 cores and the followers occupy a single core each. So moving on, we try to pack instance 3, instance 4, and instance 5 in the same manner. And here we see that all the machines are completely packed, and there are no additional buffer of resources available for these replication protocols to utilize in this case. And now we perform a similar experiment where we try to pack 5 instances of these replication protocols on larger machines with 50% write workload, targeting an in-memory key value store for about 60 seconds. And in this case, we see that in the case of Multipaxos, each instance achieves around 30K throughput compared to ePaxos, where each instance achieves only around 15K throughput. So we see this because in a resource constrained setting, ePaxos doesn't have the opportunity to utilize additional resources in order to provide this high throughput, which we have seen earlier. So for the same experiment, we now show the aggregate throughput of all the instances per second over the course of our experiment. And we see that Multipaxos ends up achieving twice the throughput of ePaxos, and this is due to high resource efficiency. But how do we actually estimate this performance impact on cloud just due to resource efficiency? So this is where our metric comes into play. Our metric, throughput per unit of constraining resource utilization, acts as a really good proxy for the performance of replication protocols in a cloud setting. So here we now compare the two graphs, normalized throughput for a single instance on a dedicated resource setting to the aggregate throughput of instances in shared resource setting. And we see how the metric actually shows us a picture of the performance of these replication protocols in a cloud setting. And we clearly see that multipaxos has better throughput. So finally, we try to compare here the throughput of replication protocol in a dedicated resource setting and the aggregate throughput of replication protocols in a shared resource setting. And we see that the optimizations proposed so far for the replication protocols definitely improve the throughput, but surely ignore the resource efficiency. And in this paper, we introduce a new metric which helps in understanding the cost of these uh, optimizations and the shifting of the load. And we hope that in the future, replication protocols will be resource optimized and when they are actually deployed on cloud. Thank you.
Okay, very nice talk. Thank you. And let me look at the Slack channel. So, okay, I'll first ask my question here. So I have a question. So can you, maybe I missed something here. So can you explain the reason of the different resource efficiency in your experiment? You mentioned you have 500% CPU utilization for 18 KOPS versus 20% CPU for 14 KOPS. So what's the reason, internal reason for this? Because of memory or disk I/O or what?
Yeah, really good question. Like in our case, the reason is just the complexity of the protocol itself, right? So if we look at how multipaxos operates, there is this one leader that pretty much carries out all the logic of the protocol, most of the logic of the protocol, right? And also communicates with the clients. The followers in multipaxos, they are kind of relatively stupid because, like, to ensure safety, they pretty much just need to receive the message from the leader, perform like one comparison to check the term number, more or less, and then reply back to the leader. If we look at ePaxos, it goes away with the single leader kind of idea because it is the bottleneck in a system, right? If you consider this dedicated setup. So what they do is they say every server, every node can be a leader. So now every machine can serve the client request, right? But this adds quite a lot of complexity in terms of ensuring the safety, because now you don't have this centralized leader who always knows of the most recent state. So now you need to add logic, and ePaxos adds logic to detect conflicts. What if two concurrent commands that arrive at two different nodes are trying to modify the same, let's say, key in a key value store, right? So now they build this additional logic that is used to exchange the dependencies and construct the dependency graphs, right? And look for the loops in this graph that would indicate of a conflict, and then resolve the loops in one way or another, right? Which usually, like in case of ePaxos, the resolving of this conflict loop will require more communication. So this adds a lot more complexity just to ensure the safety, and that's why we see the high resource utilization, higher CPU utilization.
Okay, great. So another follow-up question is, so other than the AWS cloud, did you do any other experiments in very large scale, maybe different clouds for the problem? Yeah.
Yeah, not at this point, right? We haven't really tried to confirm it at the larger scale. So the experiment in the paper where we use, well, 5 8-core machines is the biggest one that we've actually tried to run. That being said, I mean, you can look at how like big distributed databases operate, right? So that was one of the questions that we were trying to answer. Why, products like CockroachDB, YugabyteDB, MongoDB, Google Spanner, why do they rely on relatively simple, like leader-based protocols and not on some of the most sophisticated algorithms that are very popular in academic literature, but somehow don't get the adoption? And like these systems, they operate at a tremendous scale, right? So the scale of, let's say, Google Spanner or Yuga Byte is going to be way more than just 5 machines and like 5 instances. They run hundreds and possibly thousands of instances of Raft in that case for Yuga Byte. That seems to work fine for them.
Okay, great. Thank you. And we have 2 more questions here on the Slack channel. So the first question is from Raju from FIU. So in what cases do you anticipate that multiple instances of replication protocols running on a single node may be a common requirement in cloud virtual machines? Or do you believe this is more likely across virtual machines?
I honestly think that this is common now. Like it is common to pack these protocols. That's what the industry is doing. And part of the argument for this paper is that people in academia have to catch up and have to do a little bit more when we design these new protocols to actually adjust to this reality that dedicated servers or dedicated virtual machines are no longer the norm. I'm not sure if I answered the question exactly, but.
Okay, great. And so one more question from Sudarsan from Rutgers University. And so I'm curious if the resource efficiency observation between the 2 platforms you had hold when there is a frequent change of leaders.
Yeah, that's a really good question. Obviously, the leader change is a complicated and expensive procedure in protocols like Raft and multi-access. The complications obviously arise because this leader change, it needs to be safe, right? So there is quite a bit of synchronization involved, and oftentimes, especially like in case of multi-access, there is quite a bit of data movement as well because the new leader needs to learn of like all the previous stuff that was kind of in between, right? So that have possibly reached the majority but haven't been like committed yet, fully finalized. So it definitely adds to the cost of this. And for some systems that actually implement like a more traditional access approach without a stable leader, that do rely on this leader election phase to more or less give the illusion of kind of multi-leader approach where the write can come into any node, run through this leader election, commit, and then maybe some other write goes to a different node and takes the leadership away from the previous one and commits. That will probably drastically change the picture of efficiency in a Paxos-like protocol. But that being said, the more common way of implementing Paxos is multi-Paxos. And it's also the same way pretty much that the Raft is doing. We have a stable leader, and that's the premise for the efficiency here.
Great, thank you, Alexei, and very nice talk. And so we are looking forward to your following work on this topic. Thank you so much.
Thank you.
Okay, so our last speaker is Liana Valdez. She's going to present scalable but wasteful current state of replication in the cloud. So another paper and related to replication. So Liana is currently a PhD student in computer science at Florida International University. Her research interests include storage systems, distributed systems, operating systems, and so on. So now please play the video.
Hello everyone, I'm Liana Valdez from Florida International University. Today I will be presenting our work titled Unifying the Data Center Caching Layer. I will consider if such unification is feasible, and if so, would it be profitable? Computer data center nowadays consume storage using different storage types or interfaces, such as block, file, object, and key value. To accelerate performance, cloud data centers often deploy different types of caches. Such caches typically target a specific storage type, store instance, or simply workloads running on a single host or VM. On the right side, we see a typical software ecosystem for cloud computing, where we have applications and libraries that access different storage systems using different interfaces and are accelerated by distributed caching solutions. At the same time, new technologies such as 3D cross-point memories and NVMe SSDs are also becoming increasingly available. Each of these devices impose new requirements when used for caching. On the network side, high-performance network fabrics such as 40 gigabit Ethernet, Rocky, and InfiniBand are making data access over the network more efficient. In the rest of this presentation, we'll motivate our work, provide an overview of the proposed caching as a service solution. I will then present some results for a preliminary study to evaluate the advantages of our design. And finally, I will briefly discuss future work directions. Cloud data centers today run multiple applications using different storage system types. Applications running on each system typically have access only to the cache resources assigned to that host. As a result, cache resources get fragmented across different storage systems and also potentially across different nodes in the data center. Since these resources are expensive, a new solution that allows sharing all the available cache resources in the data center across storage systems and applications is desirable. Second, a majority of storage caching solutions implement write-through or write-around caching policies, thereby having no cache performance gains for write operations. However, write-dominant workloads in the cloud are commonplace. Among the collection of workloads analyzed in this paper, we find that block and object stores have 71 and 40.5% of writes, while key value and file have 22.5 and 9.8% respectively. Therefore, a storage caching layer that is unable to cache writes is likely to be limited in its effectiveness. Lastly, the diversity on caching devices that are getting deployed in the data center requires implementing optimizations for a specific cache device characteristics. This further motivates creating new caching algorithms once within a unified caching service instead of repeating these optimizations for multiple siloed solutions. To estimate the penalty of serving writes from the storage backend instead of the cache, we created a simple model where an application accesses a local and remote cache with block storage over the network. When the storage backend latency is 1 millisecond, the amount of throughput that is available for the application increases by 10 and 7 times respectively for local and remote caches, when the cache hit rate increases from 90 to 99%. Similar improvements are seen for larger storage latencies. Therefore, large performance improvements of using relatively higher performing local and remote caches sustain regardless of the backend storage latency. Next, we evaluate the performance benefits available when using higher capacity remote cache in comparison to a limited capacity local cache. When compared to a 10 GB local cache, increasing the size of the remote cache allows throughput increase of 1.24 times when increasing the cache size to 20 GB. And 18.7 when increasing the cache size to 100 GB, both at a queue depth of 8 IOs. This demonstrates that despite the added overhead of network access, there are significant performance gains to be had with larger capacity remote caches. To address these challenges, we propose in this work caching as a service, CaaS, a general distributed caching layer that abstracts and exposes all the available cache resources in the cloud for all types of storage systems. Typically, workload generators, including VMs, containers, and applications, access data residing in the backend storage over the network. Our proposed CaaS solution adds a CaaS client that interposes between the applications and the storage backend. This layer translates the storage-specific request into CaaS type request using the translation layer. CaaS clients communicate with CaaS data servers to access data. These data servers and the access to the CaaS service itself is managed by the CaaS coordination service that is implemented using a Zookeeper cluster. The CaaS coordination service manages metadata and controls cache allocation, load balancing, and fault tolerance across CaaS data servers. CaaS misses and asynchronous write-back calls are implemented by communicating with the storage backend through the CaaS client. CaaS client and CaaS data servers can run on different hosts, in which case all CaaS data access incur a network hop, but they can also be implemented as containerized services running on the same host. The CaaS API is designed around the concepts of store and CLICE. Store is the unit of access protected cache provisioning, and CLICE is the unit of CaaS data access. CaaS clients initially register with the coordination service which provides cache allocation and a map of classes and class locations for data being accessed from the storage backend if available. This map gets updated by the coordination service as the data items get accessed and the cache gets populated. Cache clients also request class location in case of not having them locally, using on-demand lookup calls to the coordination service. The cache clients communicates with cache data servers to access data using read, write clean, and write dirty operations. Of these, the write clean, dirty operations inform the data server as to whether the data being written into the cache is clean in case of the cache insertion or dirty in case of a cache update. Finally, write back calls atomically write interdependent dirty data to a storage backend to ensure that the storage backend can perform consistent point-in-time snapshots for disaster recovery. We conducted a preliminary study using 363 block storage workloads from production systems. Details of these workloads are in the paper. We simulated cache network access corresponding to 40 gigabit network and storage access corresponding to AWS EVS with 2 milliseconds higher latency. We used the ARC cache replacement algorithm for comparing local cache performance and cache performance. Using ARC, we obtained the number of read hits. All writes in local cache are misses, while all writes in cache are hits, either insertions or updates. Finally, writes to the cache layer are fault tolerant, simulated using primary backup replication operations. We model a local cache system where an application's accesses local SSD-based cache, incurring 5.3 microseconds for reads. It uses the write-through policies, so all writes are simulated misses. The cache miss latency is 2 milliseconds for accessing a block storage backend. With cache, reads incur 13.3 microseconds network round trips. Writes incur 4 network hops for accessing a leader and a single follower of the replication group servicing the write. In this first set of results, we compare the average read and write I/O latency across the 363 production storage workloads. We find that there are improvements available in cache due to its larger capacity relative to the local cache. We varied the cache size of a local cache up to a maximum of 10% of the workload footprint and a remote cache up to 20%. Read latencies are similar when the size of the local cache and cache are the same, with cache latency reducing up to 6% when we increase the cache size in cache to 20%. In the case of writes, cache using the write back policy and primary backup replication scheme reduces latency by as much as 90% relative to the local cache, which must write all data to the high latency backend storage. In this next plot, we present the overall I/O latency for the same workloads. We can see 31% reduction in average I/O latency when local cache and cache are sized to 10% of the workload footprint, with additional improvements up to 36% when the cache size is increased to 20%. As future work, some of the challenges in cache include addressing the fault tolerance and consistency requirements for having a caching solution that supports caching writes. Also, selecting the class sizes in cache is the cache small unit of access represents the trade-off to optimize for both cache fragmentation and metadata overhead at the coordination service side. In addition, the design of an allocation scheme, the corresponding eviction strategies, as well as the data placement and load balancing policies across different cache data servers are also important design decisions in cache. Finally, another goal in cache is the design of a distributed cache resource allocation algorithm that guarantees user-defined level of quality of service to the application. We would like to thank the National Science Foundation for funding the research, member of the Systems Research Laboratory, and other collaborators at Florida International University. Thank you.
Thank you. Very nice talk. Let's check the questions on the channel. Okay, so we have a bunch of questions. So the first question is from Bartley, Ivan Research. So any reasons why the percentage of writes for block store is high, but low for files, which is less than 10%? Could you detail how this metric was measured? We cannot hear you, sorry. Can you unmute yourself?
Thank you for the question. For the case of the file systems, we have the OS page cache, normally in production servers, that will capture some of the read and writes. And in case of, for the question that how this metric was calculated or measured, so all of these workloads are production workloads. So we simply counted the number of requests that we have for writes and reads in the traces.
Okay, so great. And the next question is from Phil and Dell Technologies. I see the SLAs are future work, but can you share any thoughts on implementing SLAs so clients have bounded latency? Actually, that's also related to my question. So any impact on tail latency?
So so one of the goals in our original design is to also provide quality of service for the application. And so we don't have a actual design completed for that, but as any thoughts, I think we might have we might use some work that is already done for local SSD-based cache, in which they use some partition techniques for assigning a specific cache size for specific applications, and also they have a way of converting latency curves or throughput curves for assigning resources and give a specific value of latency, requirement for an application.
Okay, and next question is from Alexei, University of New Hampshire. How do you approach tenant isolation in shared cache? If some client service overtakes the cache, this can increase cache misses for other tenants, forcing other tenants downstream service to absorb the cache misses. Any comments?
So you're saying if a specific client can overtake the cache. So I guess this, from what I can see so far, this could not happen in our design. So we assign resources for a specific client and the applications that are using the cache. So the isolation is at the level of the client service. So I don't see this happening, but yeah.
Okay, let me see any other questions. So I have my last question. And so to use CAS, what change do you require on existing data centers? I think you need some change on both client and data server side, right, to install the APIs. Is that all?
Yeah. So from the application side, we need to. So the application needs to be aware of CAS, the API with the CAS client, and on the server side. So our design needs to so homogeneously use all the servers for implementing the shared cache layer. But from the point of view of the API with respect to the storage systems, I don't see any changes. Yeah.
Okay, great. Very nice work and an excellent talk. Thank you so much.
Thank you.
So with that, we conclude this session. So for all presenters, thank you for the very great talks. Please check the Slack channel to see any remaining questions, if any. So thank you all for attending this session. And Phil, I think you want to wrap up today's program, right? Phil? Oh, great. Thank you.
Yes. Oh, thank you. And Egypt and I will join. So first of all, I want to thank our keynote speaker and all of our session chairs and all the authors for giving us very interesting
I think somehow the Philippines sign out. Welcome back.
Not sure what happened there. Anyway, I was just thanking
back, Phil.
the smooth set of presentations today. And besides the little glitch, I think the organizers have done a very excellent job today and have handled some small issues very smoothly in the background. I just want to highlight our plans for tomorrow and encourage everyone to join us again. So we begin with session 3 about new technologies. Our first paper was the best presentation award winner. So hope everyone can come and enjoy that presentation as well as the other papers in that session. And then after a break, we have an exciting panel from ideas to products, the path of successful storage startups. We have 4 founders of storage startups. I think that'll be a very exciting panel session. And then a short break. And then we have our final session of hot storage, characterization and verification. And then at the end, we have just a few moment wrap up where Egypt and I will thank everyone and review material and present a slide or two about what's happening for 2022 for hot storage.
All right. So.
All right, have a good afternoon, evening, morning to everyone, and see you again tomorrow.
Yeah, see you tomorrow. Bye.